For nearly all of human existence, reaching 40 years old was not the norm, it was uncommon. In prehistoric populations, many lives ended in childhood, in childbirth, or from injuries and infections that today feel minor. The human body was shaped in small groups moving through uncertain landscapes, where survival long enough to reproduce was enough for evolution. Natural selection does not promise long decades of aging. It preserves what works in the present. If most humans in prehistory never reached 40, why was that the case? And what does it reveal about the kind of life our biology was originally shaped to sustain? For most of human existence, the world that shaped our species was unstable, vast, and indifferent to individual survival. Anatomically, modern humans emerged in Africa roughly 300,000 years ago during the Pleistocene epoch, a period marked by repeated cycles of glacial advance and retreat. These climate shifts did not simply alter temperature. They reshaped landscapes, shifted animal migrations, changed the availability of plants, and forced small human groups to move continually in search of food and water. In such an environment, daily life was organized around immediate survival rather than long-term security. When we ask why most humans in prehistory never reached 40, we must first understand the ecological pressures that framed every stage of life from birth onward. Early human communities were small, often numbering a few dozen individuals, and mobility was essential. Remaining too long in one place risked exhausting local resources. Movement required energy, exposed individuals to unfamiliar terrain, and increased encounters with predators or rival groups. The environment offered no stable surplus. Food availability fluctuated with seasons, droughts, and animal patterns. Periods of abundance could quickly give way to scarcity. Under these conditions, survival to adulthood was already an achievement shaped by chance and resilience. The human body evolved within this pattern of uncertainty. Natural selection favored traits that increased the probability of surviving long enough to reproduce, not traits that ensured decades of comfort afterward. Energy allocation within the body reflects this priority. Growth during childhood, the onset of puberty, and reproductive capacity were biologically urgent milestones. Long-term tissue repair, protection against age-related degeneration, and the slow maintenance of cellular systems beyond midlife were not under strong evolutionary pressure if most individuals did not consistently reach advanced ages. In the Pleistocene landscapes where Homo sapiens first spread beyond Africa into Eurasia, dangers were not abstract. Large predators such as lions, hyenas, and later Ice Age carnivores occupied overlapping territories. Injuries from hunting large animals could be severe. Even minor wounds risked infection in the absence of antiseptic treatment. Exposure to cold climates during glacial phases introduced additional strain. Archaeological evidence from early sites reveals signs of healed fractures and joint stress, indicating that some individuals survived serious injuries, likely aided by social support. Yet these same skeletal remains also show patterns of trauma that could have ended many lives prematurely. The environment did not need to be catastrophic to shorten lifespan. It only needed to be consistently demanding. Infant survival was particularly fragile in such settings. High rates of childhood mortality lower the average age at death in any population, even if some adults lived into their 50s or beyond. When researchers estimate life expectancy in prehistoric groups, they often find averages that fall below 40 years. This does not mean that the human body was incapable of reaching that age. It means that the combination of environmental hazards, infectious disease, nutritional stress, and limited medical intervention made it statistically uncommon. The evolutionary context is crucial. Our ancestors did not evolve in settled cities with stored grain and controlled water supplies. They evolved in shifting ecosystems where survival depended on cooperation, adaptability, and physical endurance. The pressures that shaped the human genome were concentrated in early and midlife. The later decades that many people experience today were rarely a stable or predictable phase of existence in deep prehistory. Understanding this ecological background allows us to approach the central question with greater clarity. If most humans in prehistory did not reach 40, the answer is not found in a single cause, but in the cumulative weight of an environment that demanded constant resilience from bodies designed for immediate survival rather than extended longevity. The instability of the prehistoric environment did not only shape where humans moved, It shaped how their bodies distributed energy across a lifetime. In small hunter-gatherer bands, survival depended on a delicate balance between effort and return. Calories obtained from foraging or hunting had to cover immediate metabolic needs, support growth in children, sustain pregnancy and breastfeeding, and fuel constant physical activity. There was little margin for long-term biological investment beyond what was necessary for reproduction and short-term survival. When considering why most humans in prehistory never reached 40, it becomes important to examine how energy constraints quietly influence the aging process itself. The human body is not a machine built for indefinite repair. Cellular maintenance requires resources. Repairing damaged DNA, replacing worn tissues, supporting immune defense, and maintaining organ function all consume energy. In an environment where food availability fluctuated and periods of scarcity were common, energy allocation favored processes that ensured survival in the present. Reproduction, immune response to acute threats, and rapid healing of serious injuries were prioritized. Slow, cumulative damage that might manifest decades later did not strongly affect reproductive success in a population where many individuals did not consistently live into advanced age. This pattern aligns with what evolutionary biologists describe as trade-offs. A trait that improves early survival or reproductive output can persist even if it carries costs later in life. In the ancestral environments of Africa and later Eurasia, early adulthood represented the peak of reproductive value. The biological systems that support muscle strength, fertility, and acute stress response were strongly maintained. Systems that guard against gradual degeneration beyond midlife were under weaker selective pressure. Over thousands of generations, this balance shaped a body optimized for resilience under immediate stress rather than prolonged stability into old age. Climatic variability during the Pleistocene intensified these pressures. Rapid shifts between warmer and colder phases altered vegetation and animal distributions. Archaeological records show that human groups adapted through tool innovation, social cooperation, and flexible diet. Yet adaptation did not eliminate risk. Nutritional stress left marks on skeletal remains in the form of enamel hypoplasia in teeth, indicating periods of childhood malnutrition. Repeated stress during early development can have long-term physiological consequences, affecting immune function and metabolic efficiency. Such early life hardships increase vulnerability to disease and may shorten lifespan, even if an individual survives into adulthood. The structure of prehistoric populations further reinforced this pattern. With high rates of infant and juvenile mortality, the age distribution skewed heavily toward the young. In a community where many members were children or young adults, relatively few individuals occupied later decades. This demographic structure influenced social roles, knowledge transmission, and labor patterns. Elders existed, and ethnographic studies of some modern hunter-gatherer societies demonstrate that individuals can live into their 60s or beyond under similar subsistence modes. However, the proportion of such individuals remained smaller than in modern industrial populations. The environment did not reliably support large numbers of people reaching advanced age. When researchers estimate average life expectancy for prehistoric populations, they rely on skeletal analysis and demographic modeling. These methods suggest that life expectancy at birth often fell below 40 years, largely due to early mortality. If an individual survived childhood and adolescence, their expected remaining years increased, but even then, persistent environmental hazards limited longevity. The body's biological design must be understood within this demographic and ecological framework. It was shaped in conditions where surviving to reproduce was sufficient for genes to continue. Extended post-reproductive lifespan, though possible, was not the statistical norm in many prehistoric settings. The cumulative effect of energy constraints, environmental instability, developmental stress, and demographic structure created a world in which reaching 40 was less common than it is today. This does not imply that humans were incapable of living longer. It suggests that the environment in which our species evolved did not consistently allow most individuals to do so. Beyond climate and energy limits, another quiet force shaped the lifespan of prehistoric humans: constant exposure to physical risk. In small mobile groups moving across open savannas, forests, river valleys, and later colder steppe landscapes, daily subsistence required direct engagement with the environment. Hunting large animals demanded close contact with powerful prey. Gathering exposed individuals to unfamiliar terrain, hidden hazards, and venomous creatures. Even routine movement over uneven ground carried the possibility of falls or fractures. In a world without surgical care, antibiotics, or controlled sanitation, the line between survivable injury and fatal complication was narrow. When asking why most humans in prehistory never reached 40, this persistent background of risk cannot be separated from the ecological picture. Archaeological evidence offers quiet testimony to these dangers. Skeletal remains from various Pleistocene sites show healed fractures in ribs, limbs, and skulls, suggesting that injured individuals sometimes survived long enough for bones to mend. This implies social cooperation and caregiving within early human groups. At the same time, many skeletons display trauma that likely contributed to early death. Embedded projectile points, signs of cranial injury, and degenerative joint damage reveal lives shaped by physical strain. Even when healing occurred, repeated injuries would accumulate over time, placing stress on joints and reducing mobility well before what modern societies consider old age. The body could endure hardship, but its resilience had limits. Infectious disease compounded these risks. Bacteria do not require dense cities to spread. They thrive wherever humans gather, share food, and interact closely. Minor cuts could become infected. Gastrointestinal illnesses from contaminated water or food could lead to dehydration. Parasitic infections were common in many environments and may have caused chronic weakness. While some modern hunter-gatherer societies demonstrate relatively low rates of certain epidemic diseases compared to agricultural populations, localized infections and untreated wounds would still have taken lives. Without antibiotics or advanced medical intervention, the immune system bore the full burden of defense. If it succeeded, survival continued. If it failed, life ended, sometimes quickly. Childbirth presented additional danger. For women, reproductive years carried repeated physiological stress. Pregnancy and lactation required substantial energy investment, and complications such as obstructed labor, hemorrhage, or infection could be fatal. Skeletal and ethnographic evidence suggests that maternal mortality in pre-modern contexts was significantly higher than in modern industrial societies. Each pregnancy was both a biological necessity for population continuity and a period of elevated risk. Over time, repeated reproductive stress could weaken the body, making survival into later decades less certain. These layers of risk interacted with demographic structure. In a population where infant and juvenile mortality were already high, the loss of adults in their 20s or 30s further reduced the proportion of individuals who might approach 40. Average life expectancy remained low not because no one could live longer, but because cumulative hazards across the lifespan limited how many did. When anthropologists model prehistoric populations, they often find that surviving to adolescence significantly improved an individual's chance of reaching later adulthood. Yet even then, the environment continued to present threats that modern societies have largely mitigated. Returning to the origins of our species in Africa and its later expansion across diverse ecosystems, it becomes clear that human biology was forged in this context of layered vulnerability. The genome reflects selection for flexibility, cooperation, and short-term resilience. It does not contain guarantees against infection, injury, or reproductive risk. Longevity beyond 40 was possible and did occur, but it unfolded against a backdrop where daily life carried measurable danger. Understanding this cumulative exposure to risk helps clarify why reaching 40 was less common in prehistory. It was not a fixed biological ceiling. It was the statistical outcome of living in environments where the margin for survival remained thin across every stage of life. When researchers reconstruct the age structure of prehistoric populations, one pattern appears consistently across regions and time periods. Childhood was the most fragile stage of life. In many ancient communities, a significant proportion of individuals died before reaching adolescence. This fact alone reshapes how we interpret the idea that most humans in prehistory never reached 40. The average age at death in a population is heavily influenced by infant and juvenile mortality. If many children die young, the overall life expectancy at birth drops sharply, even if some adults survive into their 50s or beyond. Understanding this demographic structure is essential for approaching the central question with clarity rather than assumption. In small hunter-gatherer bands during the Pleistocene, childbirth occurred without surgical intervention, sterile environments, or advanced monitoring. Newborns faced immediate vulnerability. Premature birth, low birth weight, congenital conditions, and infection could all threaten survival in the first days or weeks of life. Breastfeeding provided immune protection, but maternal health and nutrition influenced both milk production and infant resilience. In times of scarcity, infants were particularly at risk. Skeletal remains from prehistoric sites often reveal a disproportionate number of subadult individuals, suggesting elevated mortality before adulthood. While preservation biases must be considered, the demographic modeling of such populations consistently indicates high early life mortality rates. This early vulnerability connects directly to our species' evolutionary beginnings. Homo sapiens evolved a long childhood compared to many other mammals. Extended juvenile development supports brain growth and social learning, which are defining features of our lineage. Yet a prolonged dependency period also increases exposure to risk. Children rely on adults for food, protection, and care. If adults are injured or resources decline, children suffer first. In unstable ecological conditions, such as those of glacial cycles and fluctuating climates, the survival of young individuals becomes uncertain. A demographic pyramid heavily weighted toward the young reflects both high fertility and high mortality. From a statistical perspective, this structure lowers average life expectancy without requiring a biological limit at 40. If half of a population dies before 15, the average age at death may appear very low, even though survivors past adolescence may live decades longer. Anthropologists often distinguish between life expectancy at birth and life expectancy conditional on surviving childhood. For individuals who reach their teenage years, the probability of living into their 30s or 40s increase significantly. Nevertheless, cumulative environmental hazards continued to shape outcomes. The key point is not that human biology prevented anyone from reaching 40. Rather, the combination of high early mortality and persistent adult risk made it uncommon for most individuals within a population to do so. Ethnographic studies of some contemporary hunter-gatherer societies provide cautious comparative insight. In groups with minimal access to modern medicine, child mortality remains higher than in industrial nations, and life expectancy at birth can fall below 40. Yet adults who survive early years often live into their 50s or 60s. This pattern likely reflects aspects of prehistoric demographic structure, though direct comparison must remain careful. Environmental conditions, contact with outside populations, and ecological context differ. Still, the general principle holds. High early mortality strongly shapes population averages. When we return to the prehistoric record, it becomes evident that the phrase "never reached 40" does not imply an intrinsic biological cutoff. It reflects a demographic reality shaped by fragile childhood survival. The evolutionary environment that forged our species did not guarantee safe infancy or stable adolescence. Many lives ended before full adulthood, pulling the population average downward. To understand why 40 was less commonly attained, we must first recognize that the earliest years of life carried the greatest uncertainty. In that uncertainty lies a large part of the answer. To understand how strongly early mortality shaped prehistoric lifespan, it helps to imagine the age structure of a small mobile band tens of thousands of years ago. In such a group, children and adolescents likely made up a large proportion of the living members. Birth rates were relatively high in order to offset frequent loss. Yet each birth carried uncertainty, and not every child survived the vulnerable early years. When demographers model populations with high infant and juvenile mortality, the resulting average age at death falls dramatically, even if those who pass adolescence may live for decades. This statistical reality lies at the heart of why most humans in prehistory did not reach 40. It was not that bodies were programmed to stop at a fixed age. It was that many lives ended long before adulthood was complete. In prehistoric environments shaped by climate fluctuation and resource variability, childhood survival depended on multiple fragile conditions aligning at once. A mother needed sufficient nutrition to carry pregnancy to term and produce adequate milk. The group needed access to consistent food sources. Clean water had to be available, though clean in pre-modern contexts rarely meant free from microbial contamination. Exposure to pathogens occurred through soil, animals, and close human contact. Children's immune systems, still developing, faced repeated challenges. Some infections were survived and left immunological memory. Others proved fatal. The archaeological record offers indirect evidence of these pressures. Skeletal remains of subadult individuals frequently display signs of physiological stress. Linear enamel hypoplasia on teeth, for example, indicates episodes during childhood when growth was temporarily disrupted, often due to malnutrition or illness. Such markers reveal that early life in prehistoric settings involved repeated stress events. Even when a child survived these episodes, cumulative physiological strain could influence long-term health. Growth disruptions are associated in modern research with later vulnerability to metabolic and immune disorders. In prehistory, such compounded stress may have reduced resilience against future injury or disease, shortening lifespan further. Demographic structure also influenced social dynamics. In a population where many members were under 15, knowledge transmission relied on a smaller number of older adults. If elders died before reaching advanced age, generational overlap was limited. This does not mean there were no older individuals. Archaeological findings confirm that some humans survived into their 50s or beyond. However, their proportion within the population remained relatively small. When the majority of individuals are young, the cultural memory of the group compresses into fewer decades. This demographic compression reflects a life cycle shaped by early vulnerability rather than late biological shutdown. It is important to distinguish between maximum lifespan potential and typical lifespan realized under environmental constraint. Modern humans, even without advanced medical intervention, are biologically capable of living beyond 40. Contemporary small-scale societies without industrial healthcare demonstrate that adults who survive childhood can reach older ages. Yet the difference between potential and probability remains crucial. In prehistoric conditions, the probability of surviving early hazards was limited. Each loss in infancy or adolescence reduced the proportion of individuals who might eventually approach 40. When researchers calculate life expectancy at birth for prehistoric populations, the figure often appears strikingly low. This number reflects the combined weight of early deaths rather than a universal ceiling imposed by biology. Recognizing this helps prevent misunderstanding. The phrase, "never reached 40", describes a statistical pattern, not a rigid biological expiration date. High early mortality created a demographic landscape in which relatively few individuals accumulated enough years to enter what we now call middle age. In that landscape, the average lifespan was shaped less by the gradual processes of aging and more by the fragile threshold of early survival. The statistical weight of childhood mortality does more than lower an average. It reshapes how an entire society experiences time. In a prehistoric band where many individuals died before adolescence, the visible face of the community would have been overwhelmingly young. Children learning to walk, adolescents acquiring skills, young adults entering reproductive years, these stages dominated the demographic landscape. The relative scarcity of older adults was not necessarily because aging itself was rapid, but because fewer individuals accumulated enough years to reach later decades. When asking why most humans in prehistory never reach 40, it becomes necessary to look not only at biological vulnerability, but at how repeated early loss structured generational turnover. In small-scale hunter-gatherer groups, fertility rates needed to remain high to sustain population size in the face of mortality. Women often experienced multiple pregnancies across their reproductive years. Each birth introduced risk. Yet without sustained fertility, the group could decline. High fertility combined with high early mortality creates a population pyramid with a wide base and narrow top. In such a structure, even if some adults survived into their 40s or 50s, they would represent a minority within the living community. The majority would be clustered in younger age brackets. Over generations, this demographic pattern becomes normal. 40 would not mark a dramatic biological boundary, but it would mark an age few consistently reached. The archaeological record provides subtle confirmation of this structure. Burial sites from various prehistoric contexts often contain a high proportion of juvenile remains. While preservation conditions vary and may bias what survives, repeated findings of subadult skeletons across regions suggest that early death was a common part of life. Age estimation techniques based on dental eruption, bone fusion, and skeletal morphology allow researchers to approximate age at death. These methods consistently indicate that many individuals did not survive into what modern societies consider middle age. The distribution of ages reflects both early mortality and continued environmental risk into adulthood. Generational overlap was therefore narrower than in contemporary populations. In modern societies, it is common for grandparents, parents, and children to coexist for decades. In prehistoric settings, such extended overlap would have been less frequent. This has implications not only for demographic averages, but for social memory and cultural continuity. Knowledge transmission depended on fewer elders, and when older individuals did survive, their experience carried particular value. Ethnographic observations of modern hunter-gatherer societies show that elders often hold critical ecological knowledge, from migration patterns to medicinal plants. Yet the proportion of such elders remains smaller than in aging industrial populations. The limited number of older adults does not imply absence, but it reinforces the idea that long lifespan was not the dominant pattern. Returning to the origins of Homo sapiens in fluctuating Pleistocene environments, it becomes clear that demographic youthfulness was a structural feature of early human life. High childhood mortality compressed the age distribution, ensuring that most living members were young. Even if the biological potential to live beyond 40 existed, the probability of reaching that age remained constrained by cumulative hazards. The phrase "never reach 40" thus reflects a population-level pattern shaped by early life fragility and rapid generational turnover. It describes a world where time was measured less in decades of aging and more in cycles of birth, growth, reproduction, and frequent loss. Understanding this demographic rhythm deepens our view of prehistoric life and clarifies why 40, though biologically possible, was statistically uncommon. Reproduction stood at the center of prehistoric life, not as a philosophical idea, but as a biological necessity. In small mobile groups spread across unstable landscapes, population survival depended on the continual birth of children. Yet each pregnancy and each birth carried measurable risk. When examining why most humans in prehistory never reached 40, the physical cost of reproduction, particularly for women, becomes a crucial element. The human body evolved to prioritize successful reproduction over extended longevity. This priority shaped not only fertility patterns, but also the long-term durability of the body itself. Human childbirth is anatomically complex. The large brain of the human infant, a defining feature of our species, must pass through a pelvis shaped for upright walking. This evolutionary compromise between bipedal locomotion and encephalization creates a narrow margin for safe delivery. In the absence of surgical intervention, obstructed labor could result in fatal outcomes for mother, child, or both. Hemorrhage, infection, and prolonged labor were common risks in pre-modern contexts. Skeletal and historical data from later pre-industrial societies indicate maternal mortality rates far higher than those observed in modern medical systems. While precise rates in deep prehistory cannot be measured directly, there is no evidence to suggest that childbirth was safer in Paleolithic environments than in early agricultural societies without medicine. Pregnancy itself required substantial physiological investment. Nutrients consumed by the mother were redirected toward fetal development. In environments where food availability fluctuated, repeated pregnancies could lead to chronic nutritional depletion. Iron deficiency, for example, increases vulnerability to infection and fatigue. Calcium demands influence bone health. In a context without dietary supplementation or consistent surplus, maternal bodies bore the cumulative cost of sustaining offspring. Lactation extended this energetic burden, often for years. High fertility in a high mortality population meant that many women experienced multiple pregnancies across their reproductive span, increasing cumulative physiological strain. The evolutionary logic behind this pattern is stark. Natural selection operates most strongly on traits that influence reproductive success. If an individual survives long enough to produce and help raise offspring to independence, their genes continue. Survival decades beyond reproductive years exerts weaker influence on genetic transmission. This does not imply that older individuals lacked social value. Anthropological research suggests that post-reproductive adults can contribute to group survival through knowledge sharing, childcare support, and resource acquisition. However, From a strictly biological standpoint, the selective pressure to ensure survival beyond the primary reproductive window is less intense. In prehistoric demographic structures already shaped by high childhood mortality, reproductive age adults carried the burden of population continuity. Any mortality within this group had amplified demographic consequences. Yet the very act of reproduction increased exposure to risk. Women faced dangers in childbirth. Men, often engaged in physically demanding hunting and territorial defense, faced injury risk linked to provisioning. The reproductive phase of life coincided with peak physical strain. Surviving through multiple reproductive cycles required resilience in environments that offered little margin for recovery. Archaeological findings from skeletal remains occasionally reveal pelvic injuries consistent with childbirth stress. While direct attribution is complex, patterns of wear and trauma suggest that reproductive strain left lasting marks on the body. Even when mothers survived childbirth, cumulative stress could weaken resistance to later disease or injury. In populations without modern obstetric care, maternal mortality was a significant contributor to adult female mortality rates. This reality shaped the age distribution of communities, reducing the number of women who would eventually approach 40. When placed within the broader Pleistocene context in which Homo sapiens evolved, reproduction emerges as both the engine of population survival and a source of biological vulnerability. The body was shaped to reproduce successfully under difficult conditions. It was not optimized for minimal wear across decades beyond that task. Understanding the reproductive burden clarifies one dimension of why 40 was statistically less common in prehistoric life. The drive to ensure the next generation carried costs that the body did not always survive. The cost of reproduction was not limited to the moment of childbirth. It extended across years of repeated pregnancies, breastfeeding, and physical labor required to sustain offspring in demanding environments. In prehistoric hunter-gatherer societies, children were not raised in static households supported by stored food and medical infrastructure. They were carried across long distances, exposed to fluctuating climates, and dependent on continuous adult effort for survival. For women, reproductive years often overlapped with peak workloads, including gathering plant foods, processing materials, maintaining shelters, and caring for multiple children simultaneously. When asking why most humans in prehistory never reached 40, it is important to consider how this prolonged reproductive effort accumulated strain over time. Energy allocation within the body follows biological priorities shaped by evolution. During pregnancy, the maternal system diverts calories and micronutrients to support fetal growth. During lactation, additional energy is required to produce milk. In conditions where caloric intake was inconsistent, the body compensated by drawing on stored resources. Repeated cycles of depletion and partial recovery could influence immune strength, bone density, and overall physiological resilience. Modern medical research shows that chronic nutritional stress affects long-term health outcomes. In prehistoric contexts, without supplementation or consistent dietary diversity, such stress likely compounded across years. The archaeological record offers indirect evidence of these cumulative pressures. Skeletal remains sometimes display signs of anemia, such as porotic hyperostosis, which can be associated with nutritional deficiency or infection. While interpretation requires caution, such markers suggest that physiological strain was common. Pelvic morphology can also reveal patterns of repeated childbirth. Although precise reproductive histories cannot be reconstructed from bones alone, anthropologists infer from demographic modeling that high fertility was necessary to balance mortality. Each additional pregnancy increased exposure to obstetric complications and infection. Even if many women survived childbirth, the repeated stress could reduce longevity relative to individuals who bore fewer children. The reproductive burden also influenced male mortality patterns. While men did not experience pregnancy, their reproductive success often depended on provisioning and protection. Hunting large animals involved close-range encounters with prey capable of inflicting severe injury. Ethnographic observations of contemporary hunter-gatherers show that hunting accidents are not rare, and serious injuries can permanently limit mobility. In prehistoric contexts without advanced medical treatment, such injuries could shorten lifespan. The reproductive phase of life, therefore, coincided with heightened physical risk for both sexes, though in different forms. This overlap between peak reproductive effort and elevated mortality risk compresses the demographic window in which individuals might accumulate enough years to approach 40. Even if the biological potential for longer life existed, the probability of surviving through repeated reproductive cycles in harsh environments remained limited. Over generations, this pattern became embedded in population structure. High fertility sustained numbers, but the physical toll of sustaining that fertility reduced the proportion of individuals who would experience extended post-reproductive decades. Returning to the evolutionary origins of Homo sapiens, it becomes clear that our species' life history strategy balances prolonged childhood with significant parental investment. Extended dependency of offspring increases cognitive development and social learning, but it also intensifies parental workload. The benefits of this strategy appear in cultural complexity and cooperative behavior, yet the costs appear in cumulative strain across the reproductive years. In a world shaped by environmental uncertainty and limited medical support, these costs influence survival probabilities. 40 did not represent a programmed endpoint. It represented an age that many did not statistically reach after navigating the compounded demands of reproduction and subsistence. The reproductive system ensured the continuity of the species, but it did so by prioritizing generational turnover over extended individual longevity. Beyond the physical toll of pregnancy and provisioning, reproduction carried a more subtle evolutionary consequence that shaped lifespan in prehistoric populations. Natural selection measures success not by how long an individual lives, but by whether genes are successfully passed to the next generation. Traits that enhance fertility, early survival, and the ability to raise offspring are strongly favored. Traits that primarily benefit survival decades after reproduction exert weaker influence on genetic transmission. This principle helps explain why extended longevity was not consistently reinforced during most of human evolutionary history. When considering why most humans in prehistory never reached 40, this evolutionary weighting becomes central. The reproductive years, typically spanning from the late teens into the 30s in many traditional contexts, represented the period of greatest biological importance for gene propagation. Once individuals had successfully reproduced and ensured some degree of offspring survival, the selective pressure to maintain robust bodily repair into later decades diminished. This does not imply that older adults lacked value. Anthropological theories, such as the grandmother hypothesis, propose that post-reproductive individuals can enhance the survival of grandchildren by contributing knowledge, childcare, and food acquisition. Some demographic studies of contemporary small-scale societies support the idea that grandmothers positively influence child survival, yet even if such contributions offer evolutionary advantages, they operate within a probabilistic framework. If environmental hazards prevent many individuals from consistently reaching advanced age, the selective force preserving late-life maintenance remains moderate rather than dominant. The biological systems responsible for cellular repair and immune regulation reflect this balance. Mechanisms that protect against acute threats during youth and early adulthood are robust, because failure during these stages directly reduces reproductive success. Mechanisms that prevent gradual degenerative processes over long spans may receive less consistent reinforcement if relatively few individuals historically lived long enough for those processes to influence reproductive output. Modern biomedical research identifies trade-offs between early life growth, reproductive investment, and long-term maintenance. Rapid growth and high reproductive output can correlate with accelerated aging in some species. While humans exhibit comparatively long lifespans among primates, our extended longevity likely evolved in the context of cooperative social systems, rather than guaranteed survival into advanced age for the majority. In Pleistocene environments characterized by mobility, fluctuating resources, and persistent injury risk, the demographic window for reproduction was limited. Those who survived to reproduce transmitted genes effectively, even if they did not consistently live into their 50s or 60s. Over many generations, this pattern shaped a species whose biology supports survival through reproductive years under stress, but does not guarantee sustained protection against cumulative wear beyond that phase. The outcome is not a rigid ceiling at 40. Instead, it is a probabilistic landscape in which reaching 40 depended on surviving childhood hazards, reproductive risks, and environmental pressures that acted most strongly before and during the primary reproductive period. Archaeological evidence suggests that some individuals did live beyond 40, demonstrating that the human body is capable of extended survival. However, their relative rarity in many prehistoric samples indicates that longevity was unevenly distributed. The evolutionary logic did not require universal long lifespan to ensure species continuity. It required sufficient survival to maintain generational replacement. Understanding this evolutionary weighting clarifies why 40 was less common as a lived reality in prehistory. The biological architecture of our species reflects a long history in which the urgency of reproduction outweighed the expectation of extended old age. Longevity beyond the reproductive peak was possible, sometimes even beneficial, but it was not the primary target of natural selection across most of human evolutionary time. In prehistoric life, physical injury was not an unusual interruption. It was an expected possibility woven into daily activity. Hunting large animals required coordination, courage, and proximity to creatures capable of inflicting lethal harm. Gathering plant foods involved traversing uneven terrain, climbing, digging, and carrying heavy loads. Movement across landscapes shaped by rocks, rivers, forests, and seasonal ice introduced constant risk of falls and fractures. When examining why most humans in prehistory never reached 40, the cumulative effect of injury without advanced medical care becomes a decisive factor. A broken limb today is typically immobilized, surgically stabilized if necessary, and protected from infection. In prehistoric contexts, recovery depended entirely on the body's natural healing capacity and the support of the group. Archaeological evidence reveals numerous healed fractures in ancient skeletal remains, demonstrating that individuals sometimes survived significant trauma. This survival implies social cooperation. Injured members were likely fed, protected, and assisted during recovery. Yet not all injuries healed. Compound fractures could become infected. Severe head trauma could prove fatal. Even non-fatal injuries could permanently reduce mobility, limiting an individual's ability to hunt or gather, thereby increasing vulnerability to future hardship. The margin between survival and death remained thin. Skeletal remains from Pleistocene sites across Africa and Eurasia show patterns of trauma consistent with physically demanding lives. Rib fractures, forearm breaks often interpreted as defensive injuries, and signs of repetitive stress on joints illustrate ongoing exposure to strain. Degenerative joint disease appears in some individuals well before what modern societies classify as old age. Repeated mechanical stress, combined with nutritional fluctuation, may have accelerated functional decline. In an environment where daily subsistence required strength and mobility, even moderate impairment could compromise survival prospects. Infection magnified these risks. A wound that penetrated skin provided entry for bacteria. Without antiseptics, sutures, or antibiotics, the immune system bore full responsibility for containment. While many infections would have resolved naturally, others could spread rapidly. Sepsis, though invisible in skeletal remains, would have been a real threat. The prehistoric world did not need large-scale epidemics to shorten lives. A localized infection in a small group could claim individuals unpredictably. Environmental exposure also increased injury risk. Seasonal shifts during the Pleistocene created cycles of extreme cold and heat. Cold environments increased the likelihood of frostbite and accidents on ice. Heat stress can impair judgment and endurance. Long-distance travel to follow migrating herds or locate water-exposed groups to unfamiliar hazards. The human body evolved remarkable adaptability, yet adaptation does not eliminate risk. It merely improves odds within constraints. Ethnographic studies of contemporary hunter-gatherer populations provide cautious insight into injury patterns. Rates of accidental trauma remain significant, particularly among adult men engaged in hunting. While direct comparison to deep prehistory must be careful, these observations illustrate how subsistence strategies inherently involve physical danger. In contexts without modern healthcare, injury contributes meaningfully to adult mortality rates. Returning to the broader question of why most humans in prehistory never reach 40, injury operates not as a singular dramatic cause, but as a steady background pressure. Over years of active subsistence, small and large traumas accumulate. Some heal imperfectly, leaving lasting impairment. Others result in death. Combined with high childhood mortality and reproductive risks, injury narrows the proportion of individuals who survive long enough to approach middle age. The prehistoric environment did not require catastrophic events to limit lifespan. It required only the persistent presence of physical risk in a world where medical intervention was absent. Within that world, 40 represented an age reached by some, but statistically constrained by the everyday hazards of survival. Injury in prehistoric life did not end with the visible wound. Its deeper impact often unfolded over months or years through chronic pain, reduced mobility, and secondary complications. A fractured limb that healed at an imperfect angle could permanently alter gait. A damaged joint might stiffen, limiting range of motion. Repeated stress on knees, hips, and shoulders from carrying loads or throwing spears left subtle but lasting marks on the skeleton. When asking why most humans in prehistory never reached 40, it is not only fatal trauma that matters, but also the gradual erosion of physical capacity caused by accumulated strain. Archaeological analyses of ancient skeletal collections reveal patterns of degenerative joint disease in individuals who died in what modern societies would consider early adulthood. Osteoarthritis, characterized by joint surface wear and bone remodeling, appears in many prehistoric remains. While such degeneration does not immediately cause death, it reduces functional efficiency. In a subsistence economy where daily survival depended on physical performance, diminished mobility could compromise access to food and increase dependence on others. Social cooperation likely buffered some of these effects, yet prolonged impairment would still elevate vulnerability during periods of scarcity or migration. The absence of advanced medical intervention amplified even minor injuries. Today, a deep cut is cleaned, disinfected, and protected. In prehistoric contexts, wound management relied on natural healing processes and possibly traditional remedies derived from plants. Some ethnographic studies suggest that foraging societies possess knowledge of medicinal herbs with antimicrobial properties. However, such treatments would not always prevent infection. A wound that healed externally might still harbor deeper complications. Chronic infections can leave subtle skeletal markers, but many would have left no trace detectable thousands of years later. Their presence must be inferred from contextual understanding of pre-modern health conditions. Repetitive microtrauma also contributed to long-term wear. Activities such as digging for tubers, scraping hides, pounding plant fibers, and transporting carcasses imposed repeated stress on muscles and joints. Over years, these movements produce cumulative strain. In industrial societies, occupational overuse injuries are mitigated by rest periods, ergonomic tools, and medical treatment. In prehistoric settings, rest was often limited by necessity. Food acquisition could not pause for long recovery without risking hunger. This dynamic created a cycle in which minor strain compounded, gradually reducing resilience. Climate conditions intensified physical burden. During colder glacial phases, maintaining body temperature required additional energy expenditure. Cold environments stiffen joints and increase risk of muscle injury. Icy terrain elevates the likelihood of falls. In warmer regions, dehydration and heat stress impair endurance and coordination. Across diverse ecosystems occupied by Homo sapiens after dispersal from Africa, environmental extremes interacted with physically demanding subsistence tasks to shape daily risk. Anthropologists studying skeletal stress markers have identified patterns such as enthesopathies, where muscle attachment sites on bone show signs of repetitive strain. These markers reflect heavy, sustained physical activity. While such activity also indicates strength and adaptation, it simultaneously reveals that the body operated under continual mechanical load. Over time, sustained load accelerates tissue wear. In a population already shaped by high childhood mortality and reproductive stress, the added burden of chronic physical strain reduces the number of individuals who maintain full functional capacity into later decades. Injury therefore operates on two levels. Acute trauma can abruptly end life. Chronic strain can gradually erode the capacity required for survival. Together, they narrow the demographic window in which individuals remain healthy enough to approach 40. The prehistoric body was resilient, yet resilience has thresholds. In environments without surgical repair, physical therapy, or antimicrobial drugs, those thresholds were more easily crossed. Understanding the cumulative nature of injury deepens the explanation for why 40 was statistically less common in prehistory. Longevity depended not only on avoiding catastrophic events, but also on withstanding the slow accumulation of wear across years of unrelenting physical demand. Violence between humans formed another layer of physical risk in prehistoric life, one that is visible in the archaeological record yet difficult to measure precisely. Small mobile bands competed over territory, water sources, migration routes, and access to game. While cooperation characterized much of human survival, conflict also occurred. Skeletal remains from various prehistoric sites reveal embedded projectile points, cranial fractures consistent with blunt force trauma, and defensive injuries on forearms. These traces suggest that interpersonal violence, whether episodic or recurring, contributed to mortality in some communities. When asking why most humans in prehistory never reached 40, conflict cannot be separated from the broader landscape of risk. Violence in small-scale societies does not require large armies or organized warfare to influence lifespan. Even limited skirmishes between groups can result in fatalities among adults in their physical prime. In populations already shaped by high childhood mortality and reproductive strain, the loss of young adults further narrows the proportion of individuals who might eventually approach middle age. Demographic modeling shows that when mortality concentrates in early and mid-adulthood, average lifespan remains low even if some members survive beyond those years. The evolutionary environment in which Homo sapiens developed included both cooperation within groups and competition between them. This dual dynamic shaped social structures and survival strategies. Archaeological evidence from sites in Africa, Europe, and the Near East indicates episodes of interpersonal violence stretching back tens of thousands of years. For example, skeletal collections from late Pleistocene contexts sometimes show multiple individuals with trauma patterns suggesting conflict. Although the scale of violence varied across regions and time periods, the presence of injury from weapons confirms that physical confrontation formed part of prehistoric reality. The consequences of such conflict extended beyond immediate fatalities. Survivors of violent encounters often carried lasting injuries. A fractured skull or damaged limb could impair function long after healing. In the absence of surgical intervention, complications might arise from infections or internal damage. Even psychological stress, though not visible in bones, likely influence group cohesion and decision-making. Repeated exposure to threat demands vigilance and physical readiness, which may divert energy from long-term maintenance processes within the body. Environmental instability sometimes intensified conflict. Climatic fluctuations during the Pleistocene altered resource distribution. Scarcity increases competition. Groups forced into overlapping territories may have faced higher tension. While some archaeological periods show evidence of peaceful coexistence and exchange networks, others reveal mass graves or clustered trauma consistent with violent episodes. The variability underscores that conflict was not universal at all times, but it was a recurring possibility within certain contexts. From a demographic perspective, mortality due to violence disproportionately affects young adults, particularly males engaged in defense or hunting. When prime-age individuals die, generational overlap decreases. Fewer adults remain to reach later decades. Even if biological aging processes would permit survival beyond 40, the probability of doing so declines when early adult mortality rises. This pattern parallels what demographers observe in modern contexts affected by conflict. Life expectancy drops sharply when violence concentrates among younger cohorts. Returning to the central question, violence operates as another cumulative pressure, layered atop injury, infection, reproductive risk, and childhood mortality. It does not require continuous warfare to influence average lifespan. Intermittent lethal encounters, spread across generations, are sufficient to shape demographic outcomes. The prehistoric world was not defined solely by harmony or by constant conflict, but by a complex interplay of cooperation and competition. Within that interplay, the possibility of violent death formed part of the environment in which human biology evolved. 40, therefore, was not only limited by internal physiological factors, but also by external social dynamics that reduced the number of individuals who survived long enough to reach that age. Long before written records, Long before cities or domesticated animals reshaped the microbial landscape, infectious disease formed a quiet and constant presence in human life. It did not always appear as dramatic epidemic waves. Often it manifested as localized infections, parasitic burdens, gastrointestinal illness, or respiratory disease that moved through small groups and faded, only to reappear later. In prehistoric contexts, without antibiotics, vaccination, or controlled sanitation, the immune system stood as the primary defense. When considering why most humans in prehistory never reach 40, the steady pressure of infection becomes a central piece of the explanation. Humans evolved in close contact with soil, water, animals, and one another. Pathogens do not require dense urban populations to exist. Many bacteria and parasites thrive in small communities where hygiene is limited to natural water sources and organic materials. Minor skin wounds provided entry points for infection. Contaminated water could transmit intestinal pathogens. Zoonotic diseases, transmitted from animals hunted or scavenged, introduced additional microbial challenges. While some infectious diseases associated with agriculture and large settlements likely intensified after the Neolithic transition, pre-agricultural humans were not free from disease. The archaeological record reveals indirect evidence of infectious burden. Certain skeletal lesions suggest chronic infection, such as periostitis, which reflects inflammation of bone surfaces often associated with bacterial invasion. Dental abscesses are common in ancient remains, indicating untreated oral infections that could spread systemically. Tuberculosis, one of the oldest known human diseases, leaves characteristic marks on bone in some prehistoric cases. Although not all infections leave skeletal traces, the presence of those that do suggests that microbial threats were embedded in daily life. The immune system itself operates under energetic constraints. Mounting a strong immune response requires significant metabolic resources. Fever increases energy expenditure. Producing antibodies and inflammatory mediators draws on nutritional reserves. In environments where food availability fluctuated, immune defense competed with other biological priorities such as growth and reproduction. A malnourished child or a lactating mother may have faced reduced immunological resilience. This interplay between nutrition and immunity likely influenced survival probabilities at every stage of life. Infections need not be immediately fatal to shorten lifespan. Recurrent illness during childhood can impair growth and weaken organ systems. Chronic parasitic infections drain nutrients over years, subtly reducing strength and stamina. Even survivors of acute disease may carry lasting physiological damage. In modern epidemiology, repeated infections are associated with long-term inflammatory states that contribute to tissue wear. In prehistoric contexts, where repeated exposure was common and medical intervention absent, such cumulative effects likely reduced the number of individuals who maintained robust health into later decades. Climatic variability further shaped disease patterns. Seasonal rains can increase mosquito populations, facilitating transmission of vector-borne diseases in certain regions. Cold stress may predispose individuals to respiratory infections. Movement across ecological zones exposed groups to unfamiliar pathogens. As Homo sapiens expanded out of Africa into Eurasia, they encountered new microbial environments. Genetic evidence suggests that some immune-related genes underwent selection during these migrations, reflecting adaptation to novel pathogens. Yet adaptation does not eliminate disease. It merely adjusts the balance between host and microbe. Within this evolutionary and ecological framework, infection acted as a steady filter across the lifespan. Many children succumbed to disease before reaching adolescence. Adults faced risks from untreated wounds, respiratory illness, and gastrointestinal disorders. Even when individuals survived individual episodes, repeated infectious stress narrowed the demographic window in which they might reach 40. The prehistoric body evolved mechanisms to combat pathogens effectively enough to sustain reproduction, but not necessarily to guarantee protection across extended decades. The quiet persistence of infection forms another layer in understanding why 40 was less commonly attained in deep prehistory. Infection in prehistoric life was not only a matter of acute episodes that ended quickly in recovery or death. It often unfolded as a cycle of exposure, partial healing, reinfection, and lingering weakness. In small mobile bands, individuals lived in close physical proximity. Food was shared, tools were passed hand to hand, water sources were communal. While these practices strengthened social bonds and cooperation, they also facilitated microbial transmission. When asking why most humans in prehistory never reached 40, it is important to consider how repeated infectious stress gradually eroded resilience over time, rather than relying solely on catastrophic disease events. Parasites likely formed a persistent background presence. Intestinal worms, transmitted through soil or contaminated food, can persist in the body for years, drawing nutrients from their host. Chronic parasitic infection reduces iron levels, weakens immune response, and impairs growth in children. Although parasites rarely leave direct traces in skeletal remains, indirect indicators such as anemia-related bone changes suggest their possible prevalence. In environments where footwear was minimal and sanitation informal, soil-transmitted parasites would have been difficult to avoid. Their long-term impact may not have been dramatic in a single moment, but cumulative over years. Gastrointestinal illness represented another recurring challenge. Water sources in prehistoric landscapes were shared with animals and subject to contamination. Diarrheal disease, particularly dangerous for infants and young children, can lead to dehydration and nutrient loss. Even if a child survived repeated episodes, interrupted nutrient absorption during critical growth windows could weaken physiological systems. The demographic weight of such illnesses is significant. In populations with limited access to rehydration therapy or antimicrobial treatment, diarrheal disease remains a leading cause of childhood mortality, even in recent history. Respiratory infections also shaped survival patterns. Exposure to cold air, smoke from indoor fires in enclosed shelters, and closed living quarters could increase susceptibility to pneumonia and other respiratory illnesses. Smoke inhalation from hearths, though central to warmth and cooking, introduces particulate matter into the lungs. Over time, repeated respiratory irritation may compromise lung function, especially in individuals already weakened by nutritional stress. These factors do not guarantee death, but they increase vulnerability when combined with other environmental pressures. The immune system itself reflects evolutionary trade-offs. It must respond vigorously to pathogens, yet excessive inflammation can damage host tissues. In early human environments, acute inflammatory responses were essential for survival against infection. However, chronic low-level inflammation resulting from repeated infections may contribute to gradual tissue wear. Modern biomedical research identifies links between chronic inflammation and age-related diseases. While prehistoric individuals may not have lived long enough for late-life degenerative conditions to dominate mortality, chronic immune activation could still reduce overall physiological resilience across adulthood. Movement across diverse ecological zones during human dispersal further complicated disease exposure. As Homo sapiens expanded into Eurasia, they encountered novel pathogens to which they had limited prior exposure. Genetic studies suggest that some immune-related adaptations arose through interbreeding with archaic hominins such as Neanderthals. These genetic exchanges may have conferred resistance to certain regional pathogens, yet adaptation is partial and ongoing. Encountering unfamiliar microbial communities likely carried mortality risks during migration phases. Taken together, these infectious pressures formed a continuous background against which all other risks operated. A body weakened by parasitic burden may recover more slowly from injury. A child recovering from diarrheal disease may be less resilient to the next infection. A malnourished adult may mount a weaker immune response to respiratory illness. The interaction between infection, nutrition, and physical strain narrows the margin for long-term survival. Within this interconnected web of pressures, reaching 40 required not only avoiding acute fatal disease, but also enduring years of repeated microbial challenge without irreversible decline. The prehistoric immune system was effective enough to sustain reproduction under stress, yet the cumulative toll of infection contributed to the statistical rarity of extended lifespan in many populations. Infectious disease in prehistoric life did not operate in isolation. It interacted continuously with nutrition, physical strain, and social structure, creating a network of vulnerability that shaped survival probabilities across decades. A single episode of illness might be overcome, yet repeated exposure within an energetically constrained environment could tip the balance gradually. When considering why most humans in prehistory never reached 40, it is this cumulative interaction that becomes decisive rather than any single pathogen acting alone. The immune system is metabolically expensive. Fever raises body temperature, accelerating cellular processes and increasing caloric demand. Producing antibodies and inflammatory mediators requires protein and micronutrients such as zinc and iron. In environments where food availability fluctuated seasonally, mounting repeated immune responses competed directly with growth, reproduction, and tissue repair. A child fighting recurrent infection may divert energy from skeletal development. An adult recovering from illness may have fewer reserves to withstand the next physical injury or reproductive stress. The body, shaped by evolutionary trade-offs, prioritizes immediate survival even if long-term maintenance suffers. This interplay becomes clearer when viewed within the ecological context of early Homo sapiens in Africa and later Eurasia. Seasonal cycles determined food abundance. Periods of drought or cold reduced caloric intake. During such times, immune defense operated under nutritional limitation. Even mild infections become more dangerous in malnourished individuals. Anthropological research in recent small-scale societies shows that nutritional stress amplifies susceptibility to disease. While direct measurement in deep prehistory is impossible, the biological principles remain consistent. Infection severity and mortality rise when energy reserves decline. The archaeological record occasionally preserves indirect markers of chronic disease burden. Patterns of growth interruption in teeth suggest repeated physiological stress during childhood. Certain bone lesions indicate long-standing inflammatory processes. Yet many infections leave no skeletal trace, meaning the visible evidence likely underrepresents the true burden. Paleopathologists must infer broader patterns from limited data, but the convergence of skeletal indicators, evolutionary theory, and ethnographic comparison supports the conclusion that infectious stress was persistent. Social structure could both buffer and amplify disease impact. Close cooperation within small bands enabled caregiving during illness. Individuals unable to forage, temporarily, could be supported by others. Such cooperation likely improved survival beyond what solitary living would permit. At the same time, close proximity increased opportunities for pathogen transmission. Shared sleeping spaces, communal food preparation, and limited waste management facilitated spread. The very sociality that defines Homo sapiens as a cooperative species also sustained microbial circulation within groups. Migration patterns during human dispersal added another dimension. As groups moved into new territories, they encountered unfamiliar microbial ecosystems. Initial exposure to novel pathogens can produce elevated mortality until some degree of immunological adaptation occurs. Genetic evidence suggests that immune-related genes underwent selection during such expansions, reflecting the evolutionary importance of pathogen defense. Yet adaptation is gradual. During transitional phases, infection likely contributed to demographic instability. Over generations, this layered disease burden reduced the number of individuals who could accumulate enough healthy years to approach 40. Even if a person survived childhood infections, avoided fatal injury, and navigated reproductive risks, the cumulative toll of repeated immune activation and nutritional depletion narrowed resilience. 40 was not biologically unreachable. It was statistically constrained by a lifetime of interacting stressors in which infection played a central role. Within the evolutionary world that shaped our species, immune competence needed to ensure survival to reproduction. Sustained protection across extended decades was less consistently reinforced. The quiet persistence of disease, intertwined with every other ecological pressure, forms a crucial part of the explanation for why extended lifespan was less common in prehistoric populations. Food scarcity was not an occasional crisis in prehistoric life. It was a recurring condition woven into seasonal cycles and climatic shifts. In the Pleistocene environments where Homo sapiens evolved, abundance and shortage followed patterns dictated by rainfall, migration of herds, plant fruiting seasons, and glacial fluctuations. When food was plentiful, groups could replenish energy reserves and support growth. When it was scarce, bodies entered conservation mode. To understand why most humans in prehistory never reached 40, it is necessary to examine how repeated episodes of nutritional stress shaped survival across the lifespan. The human body evolved mechanisms to cope with scarcity. Metabolism can slow, fat stores can be mobilized, and appetite-regulating hormones adjust to preserve energy. These adaptations increase short-term survival during famine. However, energy conservation carries trade-offs. Reduced caloric intake affects immune competence, wound healing, and tissue maintenance. In children, chronic undernutrition can stunt growth and impair cognitive development. In adults, prolonged caloric deficit weakens muscle mass and reduces resilience against infection or injury. Survival may be extended temporarily, but cumulative strain increases vulnerability over time. Archaeological indicators suggest that prehistoric populations experience periodic nutritional stress. Skeletal markers such as enamel hyperplasia reveal interruptions in childhood growth, often associated with famine or illness. Isotopic analysis of bones and teeth indicates dietary variability across seasons, reflecting fluctuating access to different food sources. In some regions, reliance on a narrow range of foods during certain periods may have led to micronutrient deficiencies. Such deficiencies do not always produce immediate mortality, yet they subtly erode physiological resilience. The demographic consequences of scarcity extend beyond individual health. In years of famine, infant and child mortality often rises sharply. Pregnant and lactating women are particularly vulnerable because their nutritional needs are elevated. Reduced maternal nutrition can result in lower birth weight, which is associated with higher infant mortality. Over successive generations, repeated cycles of scarcity can maintain a population structure dominated by younger individuals, with fewer surviving into later decades. This pattern reinforces the statistical rarity of reaching 40. Energy limitation also interacts with physical labor demands. For hunter-gatherers, acquiring food required expenditure of calories through walking long distances, digging, climbing, and carrying heavy loads. During lean seasons, the energy cost of procurement may approach or exceed intake. Such negative energy balance accelerates physiological wear. Muscle wasting and reduced bone density can occur when caloric deficit persists. In a context without stored surpluses or agricultural buffers, recovery from famine depended entirely on environmental recovery. The evolutionary origins of our species in variable African landscapes conditioned our biology to tolerate intermittent scarcity. Flexibility in diet, cooperative food sharing, and mobility improved survival odds. Yet adaptation to scarcity does not eliminate its costs. Rather, it reflects a balance between enduring short-term deprivation and sustaining long-term health. Natural selection favored individuals capable of surviving lean periods long enough to reproduce. It did not necessarily optimize mechanisms for preserving bodily integrity into advanced age under chronic nutritional fluctuation. As Homo sapiens expanded into colder Eurasian regions, reliance on seasonal hunting intensified. Large game provided substantial calories when available, but hunting success was unpredictable. Climatic downturns could reduce herd populations, intensifying scarcity. In such contexts, nutritional stress compounded existing risks from infection and injury. The cumulative effect of recurring famine episodes narrowed the proportion of individuals who maintained sufficient health to approach 40. Scarcity did not impose a rigid age limit, yet its repeated pressure shaped demographic outcomes across generations. Within a world where food supply fluctuated unpredictably, extended longevity remained statistically uncommon because survival required continual negotiation with the limits of energy availability. Scarcity did not only reduce the amount of food available, it altered the quality and balance of nutrients entering the body. In prehistoric environments, dietary composition shifted with geography and season. Coastal groups relied more heavily on marine resources, inland groups on hunted animals and gathered plants, forest communities on tubers, fruits, and small game. This diversity supported adaptability, yet it also meant that micronutrient intake fluctuated widely. When certain foods were unavailable for extended periods, deficiencies could emerge quietly. To understand why most humans in prehistory never reached 40, the long-term effects of uneven nutrition must be considered alongside more visible threats such as injury or infection. Micronutrients such as iron, iodine, vitamin D, and vitamin B12 play essential roles in immune function, bone integrity, and neurological health. Inconsistent access to these nutrients weakens systemic resilience. For example, iron deficiency contributes to anemia, reducing oxygen transport and endurance. Iodine deficiency affects thyroid function and metabolic regulation. Vitamin D levels fluctuate with sun exposure, which varies by latitude and season. In high-latitude environments during glacial phases, limited sunlight combined with reduced dietary diversity may have influenced skeletal health. Although skeletal remains do not always preserve clear signatures of specific deficiencies, patterns of bone fragility and growth disturbance suggest that nutritional stress was common in certain contexts. The energetic cost of brain maintenance also shaped nutritional vulnerability. The human brain consumes a substantial proportion of resting metabolic energy. This evolutionary investment supports cognition, planning, and social coordination. Yet, it increases baseline energy demand. During famine, preserving brain function may require drawing heavily on body stores, accelerating muscle and fat loss. In children, inadequate caloric intake during critical developmental windows can have lasting effects on growth and immune strength. Even if a child survives undernutrition, compromised development may reduce resistance to later disease. These effects accumulate over decades. Seasonality further intensified nutritional fluctuation. In temperate and cold climates, winter often restricted plant availability and hunting success. Stored foods were limited before the advent of agriculture and preservation technologies. Groups adapted by drying meat or exploiting seasonal abundance, but storage capacity was finite. Extended periods of scarcity could weaken individuals across age groups. Older adults, already carrying cumulative wear from injury and infection, might have faced disproportionate mortality during such times. Thus, famine episodes acted as demographic filters, reducing the number of individuals who survived into later decades. Archaeological isotope studies reveal shifts in dietary patterns over time, sometimes corresponding with climatic transitions. These findings demonstrate flexibility, yet also underscore dependence on environmental stability. When ecosystems changed abruptly, nutritional sources could collapse temporarily. The human capacity for dietary adaptation mitigated some risks, but adaptation requires time. Sudden environmental downturns likely elevated mortality in vulnerable segments of the population. Energy allocation under scarcity also affects reproductive timing. Nutritional stress can delay puberty and reduce fertility. While this may preserve maternal health temporarily, it also compresses reproductive windows. Individuals who survived childhood famine may have entered adulthood with reduced physiological reserves, narrowing the span during which they could withstand subsequent stress. Over generations, repeated cycles of scarcity influence not only survival, but also demographic age structure. In populations where food instability is chronic, life expectancy remains constrained even if some individuals survive into middle age. The body evolved mechanisms to endure hunger long enough to reproduce, but these mechanisms operate under limits. Each episode of scarcity leaves subtle marks on tissue, immunity, and metabolic balance. Combined with infection, injury, and reproductive strain, uneven nutrition reduces the probability of sustaining health into later decades. 40, therefore, was not an unreachable biological threshold. It was an age fewer individuals attained because cumulative nutritional instability gradually narrowed the window of robust survival. Scarcity did not arrive as a single dramatic famine and then disappear. It often returned in cycles, shaped by climate oscillations, animal migration shifts, drought, or cold phases that could last for years. During the Pleistocene, glacial and interglacial transitions altered ecosystems across continents. Grasslands expanded and contracted. Forests retreated and advanced. Herds changed routes. For small mobile human groups dependent on these patterns, ecological instability translated directly into nutritional uncertainty. When asking why most humans in prehistory never reached 40, it becomes necessary to consider how repeated ecological shocks compressed survival across generations. Climatic records from ice cores and sediment layers show that environmental shifts during the late Pleistocene could occur rapidly. Temperature fluctuations altered rainfall patterns, influencing plant productivity and animal populations. In Africa, where Homo sapiens first evolved, periods of aridity fragmented habitats, forcing groups into smaller refugia or pushing them to migrate. Migration itself carries risk. Travel requires energy, exposes individuals to unfamiliar pathogens, and increases conflict potential with neighboring groups. Even when migration succeeds, it represents a response to resource pressure rather than abundance. Repeated displacement strains the body and the social structure simultaneously. Nutritional instability interacts with demographic structure in predictable ways. During prolonged scarcity, birth rates may decline, and mortality among infants and older adults may rise. These patterns are observed in historical populations experiencing famine. While prehistoric data cannot provide exact rates, similar biological responses are expected. A body weakened by chronic undernutrition is less able to recover from injury or infection. Older individuals already carrying cumulative physiological wear may be less resilient to caloric deficit. Each ecological downturn thus trims the upper end of the age distribution. Even if some adults survive, the proportion reaching later decades remains limited. Energy scarcity also shapes immune response. When caloric intake falls below metabolic demand, the body prioritizes essential organs such as the brain and heart. Peripheral systems may receive fewer resources. Immune competence declines under sustained malnutrition, increasing susceptibility to opportunistic infections. A mild respiratory illness during abundance might be survived. The same illness during famine could become fatal. These compounding interactions illustrate how scarcity magnifies other risks rather than acting independently. Archaeological evidence sometimes reflects abrupt population declines coinciding with climatic events. Settlement layers thin, tool traditions shift, and evidence of occupation becomes intermittent. While interpretation must remain cautious, these patterns suggest that environmental stress influenced demographic continuity. Groups that endured repeated scarcity may have maintained population size only through high fertility, yet this strategy reinforces a youthful demographic structure. With many births and many early deaths, average lifespan remains low even when biological potential for longer life exists. From an evolutionary perspective, flexibility in diet, cooperation, and mobility improved resilience against ecological instability. Yet adaptation does not guarantee survival across extended decades for the majority. Natural selection shaped humans to endure fluctuation long enough to reproduce, not to thrive indefinitely under repeated environmental stress. Each cycle of scarcity acted as a filter, narrowing the number of individuals who accumulated sufficient health to approach 40. When placed within the broader network of childhood mortality, reproductive risk, injury, infection, and conflict, ecological instability reinforces a consistent pattern. 40 was attainable, but statistically constrained by a world that repeatedly tested bodily resilience. The prehistoric lifespan was shaped not by a single limiting factor, but by the convergence of recurring scarcity and cumulative biological strain. Within that convergence, extended longevity remained the exception rather than the norm. When researchers attempt to understand how long prehistoric humans lived, they cannot rely on written records or census data. Instead, they turn to bones. The human skeleton, though silent, preserves clues about age, stress, disease, and injury. Through careful analysis of skeletal remains, bioarchaeologists reconstruct patterns of mortality and demographic structure. When asking why most humans in prehistory never reached 40, the evidence drawn from burial sites and fossil assemblages provides one of the most direct windows into lived reality. Age estimation in skeletal remains relies on biological markers that change predictably across the lifespan. In children and adolescents, the eruption of teeth and the fusion of growth plates in long bones offer relatively precise indicators of age. In adults, estimation becomes more complex. Researchers examine wear patterns on teeth, changes in the pubic symphysis of the pelvis, cranial suture closure, and degenerative alterations in joints. These methods do not yield exact ages, but provide ranges that allow demographic modeling across populations. When aggregated across many individuals, patterns emerge. Numerous prehistoric skeletal collections show a high proportion of individuals who died before reaching what modern societies classify as middle age. Many burials contain remains of infants and juveniles, reflecting high early mortality. Among adults, a substantial number fall within estimated age ranges of 20s and 30s. Fewer skeletons consistently display features associated with advanced age. While preservation bias and sampling limitations must be acknowledged, The recurring pattern across diverse sites suggests that reaching 40 was less common than in contemporary populations. Some well-known prehistoric sites illustrate this demographic structure. Upper Paleolithic burial grounds in Europe, for example, often contain individuals whose skeletal features indicate death in early adulthood. In Africa and the Near East, similar patterns appear, though regional variation exists. Importantly, there are also cases of individuals who clearly survived into later decades. Skeletal evidence of extensive joint degeneration, tooth loss with compensatory bone remodeling, and healed injuries demonstrate that some humans lived long enough to accumulate significant physiological wear. These individuals confirm that biological potential for extended life existed, yet their relative frequency within assemblages remains limited. Interpreting skeletal data requires caution. Not all individuals are preserved equally. Infant bones are more fragile and may decompose more readily in certain environments, potentially underrepresenting early mortality in some contexts. Conversely, burial practices vary. Some groups may not have formally buried all members, leading to incomplete demographic samples. Despite these challenges, when multiple independent sites across time and geography show similar age distributions, confidence in broader demographic trends increases. The skeletal record also reveals cumulative stress markers that inform lifespan interpretation. Enamel hypoplasia, healed fractures, arthritic changes, and evidence of chronic infection suggest lives shaped by repeated hardship. These markers do not specify exact age at death, but they contextualize the biological environment in which mortality occurred. When combined with demographic modeling, they support the conclusion that survival into later decades required enduring numerous physiological challenges. Returning to the origins of Homo sapiens in fluctuating Pleistocene environments, skeletal evidence aligns with ecological and evolutionary theory. High childhood mortality, reproductive risk, injury, infection, and scarcity leave demographic signatures. The bones reflect these pressures in aggregated form. 40 was not biologically impossible. It was visible in some skeletons. Yet the majority of remains cluster below that threshold. Through the silent testimony of ancient bones, a consistent picture emerges. The age structure of many prehistoric populations was weighted toward youth, with fewer individuals consistently reaching later decades. This empirical foundation strengthens the explanation for why most humans in prehistory did not commonly attain 40 years of age. Estimating age at death from skeletal remains is a careful process shaped by both biological insight and methodological limitation. Adult bones do not carry a precise timestamp. Instead, they display gradual changes that must be interpreted within statistical ranges. Surfaces of joints remodel with use, teeth wear down from chewing, cranial sutures slowly fuse over time. These indicators vary between individuals depending on diet, activity level, and genetic factors. When researchers compile large samples, they construct age profiles that approximate how many individuals likely died within specific age brackets. Within many prehistoric assemblages, these profiles consistently show a concentration of deaths below what modern societies define as middle age. This recurring pattern strengthens the argument that reaching 40 was statistically less common in many ancient populations. The pubic symphysis, a joint in the pelvis, offers one of the most informative adult age markers. Its surface undergoes predictable morphological changes across adulthood. By comparing archaeological specimens to documented modern reference collections, bioarchaeologists estimate age ranges such as early adulthood, mid-adulthood, and later adulthood. Although the ranges may span several years, patterns across dozens or hundreds of skeletons reveal population-level tendencies. In numerous prehistoric samples, relatively fewer individuals fall into the most advanced age categories compared to younger adult brackets. This distribution aligns with demographic models shaped by high early mortality and cumulative environmental stress. Dental wear provides another important clue. In hunter-gatherer contexts, diets often included coarse particles from unprocessed plant fibers and grit introduced during food preparation. This abrasion accelerates tooth wear. Individuals who lived longer display significant enamel loss and sometimes complete tooth loss, with evidence of bone remodeling indicating survival after teeth were gone. Such cases demonstrate that some individuals did reach older ages. Yet, when comparing the frequency of heavily worn dentition across sites, the proportion remains smaller than in modern aging populations. Tooth wear alone cannot determine precise age, but in combination with skeletal indicators it contributes to broader patterns. Joint degeneration also informs age estimation. Osteoarthritic changes accumulate over time due to mechanical stress. In many prehistoric skeletons, signs of joint wear appear even in individuals classified as mid-adults. This suggests that physically demanding lifestyles accelerated degenerative processes. However, advanced joint degeneration sufficient to classify individuals as elderly appears less frequently. The pattern does not indicate absence of old age, but rather its relative rarity within the preserved record. It is important to acknowledge the inherent uncertainty in skeletal age estimation. Adult age markers become less precise after approximately 40 or 50 years. Biological variability increases with age, making it difficult to distinguish between late middle age and advanced age reliably. Some older individuals may therefore be grouped into broader adult categories. Even accounting for this limitation, demographic reconstructions consistently indicate that a smaller proportion of prehistoric individuals reached ages beyond 40 compared to contemporary populations. The skeletal record must also be interpreted alongside environmental and evolutionary context. If childhood mortality was high, and adult life included risks from injury, infection, reproduction, and scarcity, then fewer individuals would survive long enough for advanced age markers to accumulate. The age profiles derived from bones reflect these interacting pressures. They do not represent a strict biological ceiling, but a probabilistic outcome shaped by lived conditions. When multiple sites across Africa, Europe, and parts of Asia converge on similar distributions, confidence increases that these patterns reflect genuine demographic structure rather than isolated anomalies. The bones do not speak in exact numbers, yet their aggregate testimony reinforces the conclusion that 40 was less commonly attained in many prehistoric populations. Through careful measurement and cautious interpretation, skeletal evidence adds empirical weight to the broader explanation of limited longevity in deep human history. Skeletal evidence does not stand alone. It is strengthened when combined with demographic modeling, genetic insight, and comparison to small-scale societies that live in environments somewhat closer to those of prehistory. When multiple lines of evidence converge, a clearer picture emerges of how age was distributed in ancient populations. In asking why most humans in prehistory never reached 40, it is not enough to observe individual skeletons. One must examine patterns across sites, regions, and time periods, and then interpret those patterns within the broader ecological and evolutionary framework that shaped human life. Demographic modeling uses age-at-death estimates from skeletal assemblages to reconstruct population pyramids. These pyramids often display a wide base of infants and juveniles, narrowing sharply through adolescence and adulthood. Even accounting for preservation bias, many reconstructions suggest that a relatively small percentage of individuals consistently reached what we would define as middle age. When infant and child mortality rates are high, life expectancy at birth declines, and fewer individuals accumulate enough years to reach 40. These models do not rely on a single site. Rather, they aggregate findings from multiple archaeological contexts, reducing the likelihood that observed patterns result from local anomaly. Genetic evidence offers an additional perspective. Human longevity has a heritable component, but extreme lifespan variation is relatively modest without modern medical intervention. Comparative studies of present-day populations living with limited access to industrial healthcare show that while some individuals reach their 60s or beyond, average life expectancy remains strongly influenced by early mortality and environmental stress. These contemporary analogues must be used cautiously, since modern groups are not direct replicas of prehistoric societies. However, they provide insight into how human biology performs under subsistence conditions without advanced medicine. The general pattern persists. Survival into later decades is possible, yet not universal. Cross-species comparison also provides context. Humans live longer than most primates, particularly when juvenile mortality is accounted for. This suggests that extended lifespan has evolutionary roots. Cooperative social structures, shared childcare, and knowledge transmission likely contributed to selection for longer post-reproductive survival compared to other mammals. Yet relative longevity does not imply that most individuals in prehistory consistently reached advanced age. A species can possess a high maximum lifespan, while most members die earlier due to environmental pressures. The difference between potential and realized lifespan is central to understanding prehistoric demographics. When skeletal age distributions, demographic modeling, ethnographic comparison, and evolutionary biology are considered together, they reinforce a consistent conclusion. Biological capacity for survival beyond 40 existed. Evidence of individuals with advanced joint wear, healed injuries, and long-term adaptation confirms this. However, the proportion of such individuals within prehistoric populations was limited by cumulative stressors across the lifespan. 40 emerges not as an imposed ceiling, but as a statistical threshold fewer individuals crossed. It represents an age beyond which survival required enduring childhood vulnerability, reproductive strain, injury risk, infectious burden, nutritional instability, and social conflict. Each factor alone might not prevent reaching 40. Together, they narrowed the demographic window. The skeletal record, supported by modeling and comparative data, does not depict a humanity incapable of aging. It depicts populations shaped by high early mortality and persistent environmental risk. In such populations, extended middle age was visible but not dominant. Understanding this layered evidence moves the explanation beyond speculation. It grounds the idea that most humans in prehistory did not reach 40 in empirical observation rather than assumption. Through bones, models, and biological principles, a coherent narrative forms. Longevity was possible, but statistically uncommon in the ecological conditions that shaped our species. Aging in prehistoric life did not begin at what modern societies label as old age. It began much earlier, unfolding gradually through accumulated stress, repeated injury, infection, and nutritional fluctuation. The biological processes associated with aging cellular damage, reduced tissue repair, gradual decline in organ efficiency operate throughout the lifespan. In environments where daily survival required constant physical exertion and resilience against microbial threat, these processes may have advanced more visibly by the third or fourth decade of life. When asking why most humans in prehistory never reached 40, it becomes necessary to examine how aging itself may have manifested differently under sustained environmental strain. The human body repairs itself continuously. DNA damage occurs regularly due to metabolic activity and environmental exposure. Proteins degrade and are replaced. Cells divide and accumulate minor errors over time. In conditions of stable nutrition and medical support, these repair systems can maintain functional capacity for many decades. In prehistoric contexts, however, repeated caloric deficits, infection, and physical trauma likely diverted resources away from long-term maintenance. When energy is limited, the body prioritizes immediate survival functions. Cellular repair mechanisms may operate less efficiently under chronic stress. This does not create a fixed expiration date, but it can accelerate visible signs of physiological decline. Archaeological evidence suggests that degenerative joint changes often appeared in individuals estimated to be in their 30s. While heavy physical labor contributes to such patterns, chronic inflammation from repeated infection may also play a role. Modern research identifies inflammation as a contributor to tissue degeneration. In prehistoric populations exposed to frequent pathogens and injury, inflammatory responses would have been regularly activated. Even if each episode resolved, the cumulative effect of repeated immune activation could influence long-term tissue integrity. The process would not resemble sudden collapse, but gradual narrowing of physical capacity. Endocrine function also interacts with environmental stress. Hormonal regulation of metabolism, growth, and reproduction responds dynamically to nutritional and social conditions. Chronic stress elevates cortisol levels, which in excess can impair immune response and tissue repair. While direct measurement in prehistoric individuals is impossible, biological principles suggest that persistent environmental threat influences hormonal balance. Sustained stress may subtly reduce resilience over time, increasing vulnerability to subsequent illness or injury. The concept of aging in this context differs from modern perception. Today, many individuals experience a prolonged middle age characterized by relative stability and health. In prehistoric settings, The transition from youthful vigor to reduced physical capacity may have occurred earlier for many. A hunter with reduced endurance in his mid-30s might struggle to contribute equally to group subsistence. A woman weakened by repeated pregnancies and nutritional stress might face declining resilience before reaching what we now consider midlife. The demographic record reflects this compression. If cumulative stressors reduce functional capacity earlier, then the proportion of individuals surviving into later decades decreases. The evolutionary environment in which Homo sapiens emerged did not guarantee extended middle age. It favored robustness during peak reproductive years. Beyond that window, maintenance systems were not necessarily reinforced strongly enough to counteract decades of accumulated strain under harsh conditions. It is important to emphasize that aging itself was not dramatically faster in an absolute biological sense. Rather, environmental pressures magnified its effects. The body, shaped by trade-offs, could endure much. Yet in a world of repeated stress, the threshold at which accumulated damage translated into mortality likely arrived earlier for many individuals. 40, therefore, was less commonly attained not because aging abruptly accelerated at a fixed point, but because the visible consequences of cumulative strain often emerged before that age. Aging is not a single event, but a gradual accumulation of microscopic changes that unfold from early adulthood onward. In modern settings, many of these changes remain buffered by consistent nutrition, medical intervention, and reduced physical strain. In prehistoric environments, however, the same biological processes operated without those buffers. Cellular damage from metabolic activity accumulated in tissues exposed to constant stress. Repair systems, though robust, functioned within energetic limits shaped by fluctuating food supply and recurrent infection. When considering why most humans in prehistory never reached 40, it becomes important to examine how the balance between damage and repair may have shifted under sustained environmental pressure. At the cellular level, oxidative stress results from normal metabolism. Reactive oxygen species can damage proteins, lipids, and DNA. The body contains antioxidant systems and repair enzymes to counteract this damage. Yet chronic undernutrition reduces availability of micronutrients required for these protective systems. Vitamins such as C and E, along with trace elements like selenium and zinc, support antioxidant function. In environments where dietary intake varied seasonally, antioxidant capacity may have fluctuated. During lean periods, repair mechanisms could operate below optimal levels, allowing incremental cellular damage to persist. Over decades, this imbalance may contribute to earlier functional decline. Telomeres, protective caps at the ends of chromosomes, gradually shorten with each cell division. While telomere dynamics are influenced by genetics, environmental stress can accelerate shortening. Modern research links chronic stress, infection, and poor nutrition to reduced telomere length. Although direct measurement in prehistoric individuals is impossible, the biological principle suggests that repeated stress exposure could influence cellular aging rates. If cells reach replicative limits earlier, tissue regeneration capacity declines. In physically demanding environments, diminished regenerative ability translates into slower recovery from injury and infection. The immune system itself undergoes age-related change. Chronic activation in response to persistent pathogens may shift immune balance towards sustained low-level inflammation. This inflammatory state, sometimes described in modern research as inflammaging, contributes to tissue wear. In prehistoric contexts characterized by recurrent microbial exposure, immune activation would have been frequent. Even if individuals did not live long enough for late-life degenerative diseases common today, chronic inflammation could still impair resilience by the fourth decade of life. Hormonal regulation interacts with these processes. Testosterone and estrogen influence muscle mass, bone density, and immune function. Nutritional stress and repeated illness can alter endocrine balance, potentially accelerating declines in physical capacity. In women, repeated pregnancies and lactation cycles alter hormonal patterns across years. In men, chronic physical strain and caloric deficit may influence reproductive hormone levels. Such shifts do not impose an abrupt limit on lifespan, but they shape the trajectory of aging under environmental constraint. From an archaeological perspective, skeletal markers of wear appear in individuals classified as early or mid-adults. Degenerative changes in joints, reduced bone density, and dental attrition indicate that visible aging processes were underway before 40 for many. These markers reflect not only chronological age but cumulative exposure to stress. The body adapts continuously, yet adaptation operates within limits set by energy and repair capacity. Returning to the evolutionary context of Homo sapiens, it becomes evident that natural selection favored systems sufficient to sustain reproduction under variable conditions. Extended maintenance beyond the reproductive peak may not have been consistently reinforced if environmental hazards limited survival probabilities before late-life decline became widespread. Aging in prehistoric settings was therefore shaped by the interaction of intrinsic biological processes and extrinsic ecological stress. 40 did not represent a sudden boundary, but it marked an age at which cumulative cellular and systemic wear, magnified by environmental pressure, had already narrowed survival prospects for many individuals. Aging in prehistoric populations was shaped not only by cellular wear, but by how visible physical decline intersected with survival demands. In environments where subsistence required strength, endurance, and coordination, even moderate reductions in capacity could have tangible consequences. A gradual loss of muscle mass, slower reaction time, or diminished sensory acuity might not be fatal in isolation. Yet within a setting defined by constant physical engagement with the environment, these small changes accumulated into meaningful risk. When asking why most humans in prehistory never reached 40, it is necessary to consider how the early stages of functional decline interacted with ecological pressure. Muscle tissue naturally decreases with age in all humans, a process known today as sarcopenia. Under modern conditions, adequate nutrition and reduced physical hazard allow individuals to compensate for gradual muscle loss. In prehistoric contexts, caloric intake fluctuated and physical labor remained constant. A hunter whose grip strength weakened slightly or whose endurance declined marginally might struggle to keep pace during long pursuits. A gatherer whose balance faltered could face increased risk of falls. These shifts would not appear dramatic, yet survival margins in subsistence economies were narrow. Small decreases in performance could translate into reduced contribution to group provisioning, increasing vulnerability during lean periods. Sensory decline also plays a role. Vision and hearing subtly diminish over time. In industrial societies, corrective lenses and medical interventions mitigate these changes. In prehistoric settings, uncorrected visual decline could impair hunting accuracy or environmental awareness. Reduced hearing sensitivity might affect detection of predators or coordination within the group. Such changes typically emerge gradually during adulthood rather than suddenly in advanced age. In a world where survival relied on constant alertness, even modest sensory reduction could compound other risks. Dental health offers another example of how early functional decline influences longevity. Tooth wear was common in hunter-gatherer populations due to abrasive diets. Loss of molars reduces chewing efficiency, which in turn affects nutrient absorption. Individuals with significant tooth loss may have shifted towards softer foods, potentially limiting dietary variety. In some skeletal remains, bone remodeling around tooth sockets suggests survival after tooth loss, indicating that social support may have mitigated this challenge. Yet prolonged impairment of mastication could contribute to nutritional vulnerability, especially during scarcity. Functional aging interacts closely with social structure. Cooperative care within small groups likely allowed individuals with declining strength to remain integrated and supported. Ethnographic research suggests that elders in hunter-gatherer societies often contribute knowledge and childcare even if physical capacity decreases. However, the proportion of individuals reaching a stage where such roles predominate appears limited in many prehistoric assemblages. When cumulative stress reduces physical resilience earlier, fewer individuals progress into extended late adulthood. The evolutionary shaping of human life history favored robust performance during the primary reproductive window. After this phase, biological investment in repair may have been less strongly selected if environmental hazards curtailed survival beforehand. Aging, therefore, did not function as a distinct endpoint, but as a gradual narrowing of physiological margin. In contexts without medical support or technological buffering, this narrowing likely manifested earlier in functional terms. 40, within such a landscape, marked not only a chronological age but a threshold by which accumulated physical wear, sensory decline, and reduced regenerative capacity had already influenced survival probability. Extended middle age required enduring years of environmental demand without crossing that narrowing threshold. Many individuals did endure, as skeletal evidence confirms. Yet across populations, the cumulative effect of early functional decline interacting with ecological risk contributed to the statistical rarity of reaching 40. Aging in prehistory was not dramatically faster in biological time, but its consequences were amplified by the demands of survival. The structure of prehistoric communities shaped how lifespan unfolded across generations. Small bands of hunter-gatherers were not merely collections of individuals but interconnected networks in which survival depended on cooperation. Within these groups, age distribution influenced social roles, decision-making, and the transfer of knowledge. When asking why most humans in prehistory never reached 40, it is necessary to consider how generational turnover affected the visibility and function of older individuals within the group. In populations characterized by high childhood mortality and cumulative adult risk, the demographic pyramid remained broad at the base and narrow toward the top. Many children were born, fewer survived into adulthood, and fewer still progressed into later decades. This structure limited the number of individuals who could assume long-term elder roles, yet it did not eliminate them. Archaeological and ethnographic evidence suggests that some individuals did survive well beyond their reproductive years, and when they did, their presence carried social significance. Older adults often possessed ecological knowledge accumulated through decades of experience. They remembered seasonal patterns, migration routes, plant locations, and techniques for tool production. In small groups navigating fluctuating environments, such knowledge could enhance collective survival. Anthropological research in contemporary hunter-gatherer societies indicates that grandmothers and older adults contribute meaningfully to childcare and food processing, indirectly increasing the survival probability of younger generations. This social value may have provided some evolutionary incentive for extended lifespan relative to other primates. However, the demographic proportion of such elders remained constrained by environmental realities. If injury, infection, reproductive stress, and scarcity limited survival into later decades, then the number of experienced elders within any given band would fluctuate. Generational overlap was narrower than in modern industrial societies, where 3 or even 4 generations commonly coexist. In prehistoric contexts, overlap may have often spanned only 2 generations, particularly in periods of heightened ecological stress. This limited overlap influences not only cultural transmission but also population stability. The age structure of a group affects labor distribution. Young adults perform physically demanding tasks such as hunting and long-distance foraging. Middle-aged adults, when present in sufficient numbers, balance physical capacity with accumulated skill. When fewer individuals reach middle age, the burden of subsistence may fall more heavily on younger cohorts. This dynamic can create cycles in which the loss of experienced adults reduces group efficiency, potentially increasing vulnerability to future stressors. The prehistoric demographic pattern thus reinforced itself. High mortality in early and mid-adulthood limited the number of older individuals, and limited generational overlap constrained social buffering against environmental risk. Genetic and evolutionary theory suggests that human longevity evolved, partly because cooperative child-rearing and knowledge transfer improved group survival, yet selection for longevity operates within environmental limits. If ecological hazards consistently prevented many individuals from surviving into advanced age, the selective advantage of extremely long lifespan would be moderated. The result is a species capable of extended life under favorable conditions, yet historically shaped by environments where such conditions were rarely stable. When viewing prehistoric age structure through this lens, 40 emerges as an age that marked the transition from peak reproductive adulthood toward later life. The demographic narrowing above this threshold reflects cumulative hazard rather than abrupt biological termination. Social systems could support some elders, but the proportion of individuals who survived long enough to assume sustained elder roles remained limited. The generational rhythm of prehistoric life was therefore characterized by rapid turnover and a youthful population core, with fewer individuals consistently progressing into later decades. This demographic structure forms another layer in understanding why most humans in prehistory did not commonly reach 40 years of age. Generational turnover in prehistoric societies was not only a demographic statistic, it shaped the rhythm of social continuity and the pace at which knowledge, skills, and memory were transmitted. In a population where many individuals did not consistently survive into later decades, each generation carried the responsibility of learning, adapting, and teaching within a compressed time frame. When considering why most humans in prehistory never reached 40, it becomes important to examine how limited generational overlap influenced both survival and lifespan probability. In small hunter-gatherer groups, survival depended heavily on collective knowledge. Understanding seasonal cycles, migration routes of animals, edible plant identification, and tool-making techniques required accumulated experience. When individuals survived into their 40s or beyond, they likely functioned as repositories of ecological memory. Yet if environmental hazards reduced the number of such elders, the depth of collective memory narrowed. Knowledge would still pass from adults to children, but with fewer decades of lived experience behind it. This dynamic may have required younger adults to assume responsibilities earlier, accelerating social maturation while leaving less margin for extended middle age. The compression of generational overlap also affects reproductive timing. In societies with high mortality, individuals often begin reproduction relatively early in adulthood to ensure generational continuity. Early reproduction shortens the interval between generations. If a woman gives birth in her late teens or early 20s, and her child does the same, generational cycles turn quickly. In such contexts, the age of 40 may already place an individual 2 generations removed from infancy. Even if biological capacity allows further survival, the social structure may not anticipate extended post-reproductive decades as a stable norm. Ethnographic comparisons provide cautious parallels. In some contemporary small-scale societies with limited access to modern healthcare, life expectancy at birth remains lower than in industrial nations. Yet adults who survive early hazards can live into later decades. However, the proportion of individuals above 50 often remains modest compared to aging industrial populations. Generational overlap is present, but less extensive. These observations, while not identical to prehistoric conditions, suggest that demographic youthfulness persists where environmental stress remains significant. Social buffering could partially offset the effects of limited generational overlap. Cooperative childcare, food sharing, and mutual defense enhance resilience. Yet buffering has limits. If too many adults are lost to injury, infection, or scarcity within a short period, the social network weakens. Smaller groups face higher vulnerability to ecological shock. Population bottlenecks observed in genetic studies of early Homo sapiens may reflect such demographic contractions. While precise causes vary, repeated cycles of environmental stress and limited survival into later decades likely shaped population size fluctuations. The relationship between age structure and lifespan is reciprocal. A youthful population means that fewer individuals accumulate enough years to serve as long-term stabilizers within the group. At the same time, environmental conditions that constrain survival into later decades reinforce that youthful structure. 40 thus appears not as a strict biological boundary, but as a demographic marker rarely crossed in large numbers. The social world of prehistoric humans functioned within shorter generational arcs. Responsibilities, reproduction, and knowledge transfer unfolded under the assumption that survival beyond middle adulthood was uncertain. Understanding this compressed generational rhythm deepens the explanation for limited longevity. It reveals that lifespan patterns were embedded not only in biology and environment, but also in the social tempo of prehistoric life. Within that tempo, extended middle age remained possible, yet statistically uncommon across many populations shaped by high turnover and environmental risk. The presence or absence of older adults in prehistoric communities influenced not only social roles but also the stability of cultural knowledge over time. In groups where few individuals consistently reached later decades, each surviving elder carried disproportionate weight in maintaining memory of past events, environmental patterns, and adaptive strategies. When asking why most humans in prehistory never reached 40, it becomes important to consider how limited longevity affected the transmission of cumulative experience across generations. Knowledge in hunter-gatherer societies is often embedded in practice rather than written record. Skills such as tracking animals, recognizing edible plants, shaping stone tools, and navigating seasonal landscapes are refined over years of observation. An individual who survives into their 40s or beyond may possess insights unavailable to younger adults. Yet if demographic structure restricts the number of such individuals, knowledge must be transmitted more rapidly and perhaps with less depth. Generational compression means that fewer decades of experiential memory accumulate within a single lifetime. This does not imply that prehistoric cultures lacked sophistication. Archaeological evidence reveals complex tool industries, symbolic expression, and long-distance exchange networks. However, the social framework within which these cultural forms persisted was shaped by relatively limited generational overlap. If high mortality reduced the number of elders at any given time, cultural continuity depended heavily on efficient teaching and collective memory, rather than extended mentorship across many decades. This dynamic reinforces the idea that 40 marked a significant demographic threshold. Those who crossed it entered a comparatively smaller segment of the population. Genetic studies of ancient populations sometimes reveal fluctuations in effective population size, suggesting periods when groups contracted significantly. Such bottlenecks could result from environmental stress, conflict, or disease. When adult mortality rises during such episodes, generational overlap narrows further. Fewer individuals survive long enough to accumulate extensive ecological knowledge. The loss of experienced adults may reduce adaptive capacity in subsequent generations, indirectly influencing survival probabilities. In this way, lifespan patterns interact with cultural resilience. Social cooperation likely mitigated some effects of limited longevity. Humans evolved strong capacities for shared childcare, collective defense, and food distribution. Even if few individuals lived far beyond 40, cooperative networks allowed knowledge to circulate horizontally among adults, as well as vertically across generations. Yet the statistical rarity of extended lifespan shaped expectations within the group. Responsibilities were assumed earlier. Leadership roles may have rotated more frequently. Social hierarchies, if present, were likely influenced by age but not dominated by large cohorts of elders as seen in many modern societies. When placed within the broader context of childhood mortality, reproductive risk, injury, infection, scarcity, and conflict, generational turnover appears as both consequence and reinforcement of limited longevity. High mortality restricts generational overlap. Limited overlap influences social structure and adaptive capacity. Environmental stress then interacts with these factors to maintain a youthful demographic profile. 40 thus represents not merely a biological age but a social milestone that relatively few individuals consistently reached. Those who did may have played vital roles, yet their numbers remain constrained by the cumulative pressures shaping prehistoric life. Understanding the social implications of limited generational overlap completes another layer of the explanation. Longevity in prehistory was shaped by biology and environment, but also by the tempo of generational exchange. Within that tempo, extended middle age was visible yet uncommon, framed by a world in which survival to later decades required navigating multiple layers of risk across a compressed demographic landscape. The transition from mobile hunter-gatherer societies to early agricultural communities did not immediately lengthen human lifespan. In some regions, the shift to farming introduced new pressures that reshaped health and mortality patterns in complex ways. When examining why most humans in prehistory never reached 40, it is important to recognize that the adoption of agriculture, beginning roughly 12,000 years ago in parts of the Near East, and later spreading to other regions, did not instantly reduce early mortality or eliminate cumulative stress. Instead, it transformed the ecological and social environment in which lifespan unfolded. Agriculture allowed for more consistent food production in certain seasons, yet it also narrowed dietary diversity. Early farming populations often relied heavily on a limited number of staple crops such as wheat, barley, rice, or maize, depending on region. Archaeological isotopic analysis of skeletal remains indicates that agricultural diets sometimes contained fewer varied nutrients than those of diverse foraging societies. While caloric supply may have increased in stable harvest years, micronutrient deficiencies could emerge when diets became cereal-dominated. Skeletal evidence from early farming communities frequently shows signs of anemia and dental decay, reflecting changes in nutrition and carbohydrate intake. These shifts did not necessarily extend average lifespan beyond 40. The rise of permanent settlements also altered disease dynamics. Sedentary living increased population density. Close quarters, shared water sources, and proximity to domesticated animals facilitated the spread of infectious disease. Zoonotic pathogens, transmitted from animals to humans, became more prominent with animal husbandry. Tuberculosis, for example, is believed to have intensified in settled populations. While some hunter-gatherer groups experienced infectious burdens, early agricultural villages likely amplified transmission pathways. In this context, infection continued to constrain survival probabilities across childhood and adulthood. Child mortality remained high in many early farming societies. Archaeological cemeteries from Neolithic sites often reveal substantial numbers of juvenile burials. Life expectancy at birth may not have increased significantly compared to some foraging populations, particularly during the initial phases of agricultural adoption. Although food storage reduced some seasonal scarcity, crop failure due to drought, pests, or soil depletion could produce severe famine affecting entire communities. The stability promised by agriculture proved conditional and uneven. Labor demands also shifted. Farming required repetitive physical tasks such as planting, harvesting, grinding grain, and carrying water. Skeletal markers from agricultural populations display patterns of repetitive strain distinct from those of hunter-gatherers. While hunting injuries may have decreased in some contexts, overuse injuries and spinal stress became more common. The physical burden remained substantial, though in different forms. Chronic strain continued to influence functional capacity across adulthood, potentially limiting the proportion of individuals who sustained robust health into later decades. Demographic patterns during early agricultural periods reflect these interacting pressures. Population size often increased due to higher fertility supported by more reliable weaning foods. However, increased fertility combined with persistent mortality maintained youthful population structures. The number of individuals surviving into what modern societies classify as middle age remained constrained. 40 did not become a universal milestone simply because agriculture emerged. Instead, the shift introduced a new balance of risks and resources. From an evolutionary perspective, the agricultural transition occurred relatively recently compared to the long span of human history in foraging contexts. Human biology had been shaped over hundreds of thousands of years in mobile environments. The rapid adoption of sedentary farming did not immediately remodel physiological systems. Bodies adapted behaviorally and culturally faster than genetically. As a result, early farming communities continued to experience high childhood mortality, infectious disease burden, nutritional instability, and physical strain. The demographic reality remained one in which many individuals did not consistently reach 40. Agriculture altered the landscape of risk, but it did not erase the cumulative pressures that had long shaped human lifespan. As agricultural societies matured, new forms of organization emerged that reshaped patterns of survival. Yet these changes unfolded gradually and unevenly. Permanent settlements allowed for the accumulation of material goods, storage facilities, and eventually social hierarchies. In some regions, irrigation and crop rotation improved food reliability over generations. However, improvements in food stability did not immediately translate into extended lifespan for the majority. When examining why most humans in prehistory never reached 40, the early agricultural centuries reveal that environmental control remained fragile, and health burdens persisted in altered forms. Population density increased substantially in farming villages. While this supported cultural complexity and technological innovation, it also intensified disease transmission. Pathogens spread more easily in crowded settlements than in dispersed mobile bands. Waste accumulation near living areas contaminated water sources. Domesticated animals shared space with humans, increasing exposure to zoonotic disease. Archaeological findings from early agricultural cemeteries often display skeletal indicators of chronic infection and nutritional stress. The shift to sedentism altered risk patterns rather than eliminating them. Mortality remained concentrated in infancy and early adulthood. Diet composition further influenced health. Reliance on cereal crops introduced higher carbohydrate consumption and reduced dietary variety in many regions. Skeletal remains from early agricultural populations frequently show increased rates of dental caries compared to foragers. Carbohydrate-rich diets feed oral bacteria, leading to tooth decay and abscesses. Untreated dental infection can spread systemically, contributing to morbidity and mortality. Additionally, dependence on a limited range of crops heightened vulnerability to crop failure. Drought, flood, or pest infestation could devastate harvests, producing famine affecting entire settlements simultaneously. Such events compressed mortality into short intervals, reducing the number of individuals surviving into later decades. Social stratification also emerged in some agricultural societies. Access to food and resources became uneven. Elite individuals may have experienced better nutrition and longer survival, while lower-status individuals faced heavier labor burdens and reduced access to surplus. Skeletal evidence from some ancient societies suggests disparities in diet and workload across social categories. This uneven distribution of resources may have created pockets of extended survival within certain groups, while leaving the broader population subject to persistent risk. Thus, even as agriculture advanced, 40 remained an age that many did not consistently reach. Labor patterns in agricultural communities imposed new strains. Repetitive tasks such as grinding grain with stone tools generated skeletal wear in shoulders and wrists. Carrying water and crops produced spinal stress. These patterns appear in osteological studies of Neolithic and Bronze Age populations. Although the nature of injury differed from hunting trauma, chronic musculoskeletal strain remained prominent. Over time, such strain reduced functional capacity in adulthood. In the absence of medical intervention, long-term impairment could increase vulnerability to infection or famine. The demographic impact of agriculture therefore reflected a balance between increased fertility and persistent mortality. Population growth occurred primarily because birth rates exceeded death rates, not because individuals universally lived longer. Life expectancy at birth in many early farming societies remained below 40. Over centuries, incremental improvements in sanitation, urban planning, and trade networks gradually influenced survival patterns. However, these changes unfolded long after the initial agricultural transition. In the broader sweep of human history, agriculture occupies only a fraction of our evolutionary timeline. Human biology had already been shaped by hundreds of thousands of years in fluctuating foraging environments. The shift to farming did not immediately restructure physiological resilience. Instead, it introduced new ecological challenges layered atop older ones. Within this evolving landscape, the demographic profile remained youthful. 40 continued to represent a milestone that fewer individuals attained compared to modern populations. The agricultural era reshaped risk, but it did not yet create the conditions necessary for widespread extended middle age. Over many centuries, agricultural societies gradually developed strategies that moderated some of the risks present in early farming communities. Irrigation systems stabilized crop yields in certain regions. Storage technologies improved protection against seasonal scarcity. Trade networks expanded dietary diversity by moving goods across distances. Yet even with these advances, widespread and consistent survival beyond 40 remained uncommon for much of ancient history. The transformation from mobile foraging to complex agrarian civilizations altered the landscape of risk, but it did not eliminate the cumulative pressures shaping human lifespan. When asking why most humans in prehistory never reached 40, it becomes clear that agriculture initiated a slow transition rather than an immediate demographic revolution. Urbanization introduced both opportunity and vulnerability. Early cities concentrated population density at levels unprecedented in human history. This concentration supported specialization of labor, technological innovation, and cultural exchange. At the same time, it intensified infectious disease transmission. Historical records from later ancient civilizations describe periodic outbreaks of epidemic disease. Archaeological evidence from burial grounds reveals clusters of mortality likely linked to infectious events. Although some urban centers implemented drainage and sanitation systems, these measures were often limited or unevenly applied. For the majority of inhabitants, exposure to pathogens remained a constant reality. Nutritional patterns in mature agricultural societies displayed regional variation. Some areas achieved relatively balanced diets through mixed farming and animal husbandry. Others remained dependent on a narrow range of staple crops. Skeletal remains from ancient civilizations frequently exhibit signs of nutritional stress alongside evidence of physical labor. Anemia, dental decay, and joint degeneration persist in many archaeological samples. While elites in certain societies may have enjoyed improved survival prospects, the broader population often experienced persistent health burdens. The demographic profile in many ancient agrarian societies therefore continued to display high childhood mortality and significant adult risk. It was not until much later in history, particularly in the last few centuries, that sustained improvements in sanitation, public health, and medical knowledge began to transform life expectancy patterns dramatically. The agricultural revolution, while foundational to civilization, did not immediately generate a world in which 40 became a typical milestone for the majority. Instead, it established conditions that, over millennia, allowed gradual incremental gains. These gains were uneven, interrupted by war, famine, and epidemic cycles that periodically reduced population size. Genetic and archaeological data indicate that many ancient societies experienced recurrent population contractions. Crop failures, climatic shifts, and disease outbreaks could reverse incremental improvements. Even in complex civilizations with writing and architecture, the average life expectancy at birth often remained below 40 for much of recorded history. This continuity underscores how deeply entrenched earlier demographic patterns were. Human biology had evolved under conditions of high early mortality and environmental stress. Agricultural and urban innovations slowly modified those conditions but did not immediately override them. Thus, the age of 40 continued to represent a threshold fewer individuals consistently crossed. The shift from pre-agricultural to agrarian life marked a pivotal chapter in human history, yet its demographic consequences unfolded gradually. The body, shaped by long evolutionary experience in fluctuating environments, did not instantly adapt to sedentary life. Disease ecology changed, nutritional patterns shifted, and social hierarchies emerged. Within this evolving landscape, survival probabilities improved incrementally in some regions while remaining constrained in others. The rarity of extended middle age persisted for much of pre-modern history. Understanding this gradual trajectory clarifies that the question of reaching 40 extends beyond the Paleolithic into the long arc of early civilization. The conditions necessary for widespread longevity required further transformations that lay centuries ahead. For most of human history, whether in foraging bands or early agricultural settlements, life expectancy remained shaped by high early mortality and persistent environmental risk. The transformation that would dramatically alter this pattern began only recently in evolutionary terms. Over the past few centuries, and especially during the last 200 years, improvements in sanitation, nutrition, and medical knowledge have fundamentally reshaped survival probabilities. When asking why most humans in prehistory never reached 40, it is important to recognize how unusual the modern demographic landscape truly is. The decline in mortality did not occur all at once. In many parts of Europe and later other regions, gradual improvements in agricultural productivity during the early modern period increased food stability. Better crop rotation, expanded trade networks, and more efficient storage reduced the frequency of severe famine in certain areas. At the same time, urban infrastructure slowly improved. Clean water systems, sewer networks, and waste management began to reduce exposure to pathogens. These changes were uneven and often limited at first, but they initiated a shift in the balance between infection and survival. One of the most significant contributors to rising life expectancy was the reduction of infant and child mortality. Vaccination campaigns, beginning with smallpox inoculation in the 18th century, dramatically lowered mortality from specific infectious diseases. Later advances in bacteriology, antibiotics, and public health practices further reduced childhood deaths. When fewer infants and young children died, average life expectancy at birth rose sharply, even before dramatic changes occurred in adult longevity. This demographic shift altered the age structure of populations, increasing the proportion of individuals who survived into their 40s and beyond. Nutrition also improved in many industrializing societies. greater agricultural output, and global trade diversified diets. Access to animal protein, fruits, and vegetables increased for broader segments of the population over time. Improved maternal nutrition reduced complications during pregnancy and increased infant survival. As caloric intake stabilized, the body's capacity for immune response and tissue repair strengthened. These developments allowed biological systems shaped under ancient conditions to function with fewer interruptions from chronic scarcity. Medical innovation accelerated these trends. The discovery of germ theory clarified the mechanisms of infectious disease transmission. Surgical techniques advanced, and antiseptic practices reduced post-operative mortality. Antibiotics transformed once fatal infections into treatable conditions. While such interventions initially reached only portions of the global population, their cumulative effect reshaped survival patterns in societies where they became widespread. For the first time in human history, large segments of populations consistently survived beyond 40. It is important to emphasize that the underlying biology of Homo sapiens did not change dramatically within these few centuries. Genetic evolution operates over much longer timescales. Instead, environmental buffering increased. The same physiological systems that had long been tested by scarcity, infection, and injury now operated in contexts with greater stability and medical support. The decline in mortality was driven primarily by reduced exposure to early life hazards and improved management of disease, not by a sudden transformation of human aging mechanisms. As a result, modern life expectancy in many countries now exceeds 70 or 80 years, a dramatic departure from prehistoric demographic patterns. This contrast highlights how exceptional extended middle age and old age are in the broader sweep of human history. For hundreds of thousands of years, reaching 40 was statistically less common because environmental pressures constrained survival. Only in the recent past have social, technological, and medical systems altered those probabilities on a large scale. Understanding this historical turning point reframes the question. The rarity of reaching 40 in prehistory reflects the long evolutionary baseline of human life. The widespread attainment of later decades is a recent development, built upon layers of innovation that gradually reshaped the ecological conditions under which our species lives. As public health measures expanded and medical knowledge deepened, the transformation of lifespan accelerated in ways that would have been unimaginable for most of human history. Yet this transformation did not arise from a fundamental redesign of the human body. It emerged from layered changes in environment, technology, and collective organization that reduced the intensity of the pressures that had long limited survival. When reflecting on why most humans in prehistory never reached 40, the contrast with modern demographic patterns underscores how recent and contingent extended longevity truly is. One of the most profound changes occurred through the control of infectious disease. The development of antibiotics in the 20th century drastically reduced mortality from bacterial infections that once proved fatal. Pneumonia, wound infections, and tuberculosis, which had shaped survival patterns for millennia, became increasingly treatable in societies with access to medicine. Vaccination campaigns expanded beyond smallpox to include polio, measles, and other childhood diseases. These interventions dramatically lowered mortality rates in infancy and adolescence. As childhood survival stabilized, a larger proportion of individuals accumulated enough years to enter middle age. Improvements in maternal healthcare also contributed to demographic change. Access to trained midwives, antiseptic childbirth practices, and later hospital-based obstetrics reduced maternal mortality significantly in many regions. For most of prehistory and much of early civilization, childbirth posed substantial risk. With safer delivery and postpartum care, women increasingly survived multiple pregnancies without fatal complication. This shift allowed more individuals to progress beyond the reproductive window into later decades, altering generational overlap and social structure. Nutrition continued to improve alongside industrialization and global trade. While inequalities persisted and remain, overall caloric availability increased in many parts of the world. Refrigeration and food preservation technologies reduced seasonal shortages. Fortification of staple foods addressed specific micronutrient deficiencies. With more consistent intake of essential nutrients, immune function strengthened and chronic deficiency-related illness declined. These changes did not eliminate disease, but they reduced one of the persistent constraints that had long narrowed lifespan probability. Workplace conditions also shifted over time. Mechanization reduced reliance on continuous heavy manual labor in some sectors. Although industrial work introduced its own hazards, gradual regulation of labor environments lowered injury rates in many contexts. Medical treatment for trauma improved survival after accidents. The cumulative effect of these developments allowed more individuals to maintain functional capacity into later adulthood. For the first time, extended middle age became statistically common in certain populations. Demographic data from the 19th and 20th centuries reveal a steady rise in life expectancy at birth. Importantly, much of this increase resulted initially from reductions in early mortality rather than dramatic extension of maximum lifespan. As more children survived into adulthood, the population age structure broadened at the top. Later, advances in cardiovascular care, cancer treatment, and chronic disease management further extended survival into older decades. These innovations represent a profound environmental buffering of risks that had shaped human life for hundreds of thousands of years. From an evolutionary perspective, this shift is extraordinarily recent. The biological systems governing aging were not engineered with the expectation of widespread survival into the 8th or 9th decade of life. They evolved under conditions where many individuals did not consistently reach 40. Modern longevity is therefore not evidence that prehistoric humans were biologically incapable of longer life. It reflects the reduction of external constraints that once curtailed survival probabilities. Understanding this modern transition highlights how deeply environment shapes demographic outcomes. The rarity of reaching 40 in prehistory was not a biological inevitability, but a reflection of cumulative ecological pressures. The expansion of lifespan in recent centuries reveals how altering those pressures can transform survival patterns without fundamentally rewriting the human genome. The expansion of lifespan in the modern era did not simply add years to individual lives. It transformed the structure of entire societies. As more individuals survived childhood and progressed through adulthood into later decades, the demographic pyramid reshaped itself. The once narrow upper tiers broadened. 3 and even 4 generations began to coexist regularly. This shift marks a profound departure from the demographic patterns that characterized most of human history. When reflecting on why most humans in prehistory never reached 40, the scale of this transformation reveals how unusual contemporary longevity truly is. In industrialized societies, life expectancy at birth now often exceeds 70 or 80 years. Yet this figure must be interpreted carefully. Early increases in life expectancy resulted primarily from reductions in infant and child mortality. Once those hazards declined, average age at death rose rapidly. Later, advances in chronic disease management extended survival further into older age. Improvements in cardiovascular treatment, diabetes management, and cancer therapy reduced mortality in middle and late adulthood. These developments layered additional decades onto lifespans that had previously been curtailed by environmental pressures. The consequence of this demographic shift is visible in population age structure. Aging societies now face challenges that would have been unfamiliar to prehistoric communities. Pension systems, elder care infrastructure, and long-term management of degenerative disease. Extended lifespan has reshaped economic organization, family structure, and social expectations. In prehistoric contexts, the majority of individuals did not anticipate decades beyond peak reproductive age. In modern contexts, middle age and old age constitute substantial portions of life. This transformation reflects environmental buffering rather than sudden biological redesign. The human genome remains largely similar to that of our Paleolithic ancestors. The physiological processes governing aging, cellular repair, and immune regulation have not been fundamentally altered within a few centuries. Instead, external threats that once limited survival, infectious disease, maternal mortality, severe famine, untreated injury, have been mitigated in many regions. The body that once faced constant ecological challenge now operates within constructed systems of protection. This contrast underscores the central theme. The rarity of reaching 40 in prehistory was shaped by context rather than intrinsic incapacity. Modern longevity demonstrates that the human body possesses latent potential for extended survival when environmental pressures are reduced. Yet this extended survival also reveals new dimensions of aging. As individuals live longer, age-related diseases such as Alzheimer's disease, osteoporosis, and certain cancers become more visible. These conditions were likely less prominent in prehistoric populations not because biology prevented them, but because fewer individuals survived long enough for such diseases to manifest widely. The modern era exposes aspects of human aging that were historically less common, simply due to shorter realized lifespan. Recognizing this helps clarify that longevity is deeply contingent on ecological and technological context. For most of our species' existence, survival beyond 40 required navigating a landscape of cumulative risk. Only recently have human societies constructed environments that buffer those risks at scale. The demographic revolution of the past 2 centuries is therefore an exception in the long arc of human history. It does not negate the patterns of prehistory, but rather highlights how extraordinary the present moment is in evolutionary terms. The question of why most humans in prehistory never reached 40 finds its answer in those ancient ecological conditions. The fact that many now live decades beyond that threshold illustrates how profoundly environment shapes the boundaries of realized human lifespan. If most humans in prehistory did not consistently reach 40, and if modern longevity is a recent environmental achievement rather than an ancient biological norm, then a deeper question emerges. What does this contrast reveal about the relationship between our evolutionary design and the world we now inhabit? For hundreds of thousands of years, the human body operated within narrow margins defined by infection, scarcity, injury, and reproductive strain. Only in the last few centuries have those margins widened for large portions of humanity. This widening invites reflection on how a body shaped under one set of pressures responds to a radically altered environment. The evolutionary history of Homo sapiens forged systems optimized for flexibility and short-term resilience. Our metabolism adjusts to famine. Our immune system responds aggressively to acute infection. Our stress response prepares us for immediate threat. These traits improved survival probabilities in fluctuating Pleistocene landscapes. Yet they were not crafted with the expectation of stable abundance, low infectious burden, and extended decades beyond peak reproduction. When individuals now routinely live into their 70s and 80s, they carry biological architectures formed under very different constraints. The rarity of reaching 40 in prehistory reflects a long evolutionary baseline in which cumulative hazards limited realized lifespan. Modern longevity, by contrast, reveals the latent capacity of the same biological system when external pressures are buffered. However, this buffering does not eliminate the trade-offs embedded in our physiology. Systems optimized for short-term survival can generate long-term consequences when environmental conditions shift. For example, metabolic mechanisms designed to store energy during abundance become maladaptive in contexts of chronic caloric surplus. Immune responses tuned for acute microbial defense may contribute to inflammatory conditions when infection risk declines. These dynamics illustrate that longevity is not simply an extension of prehistoric life, but a new phase interacting with ancient biological frameworks. The expansion of lifespan also reshapes the experience of aging itself. In prehistoric contexts, cumulative wear often intersected with environmental hazard before late-life degenerative conditions could dominate. Today, reduced exposure to early mortality allows age-related diseases to surface more prominently. Osteoporosis, neurodegeneration, and cardiovascular disease reflect intrinsic aging processes that were always present but less frequently observed in populations where fewer individuals survived into later decades. The modern demographic profile exposes dimensions of human biology that prehistory seldom revealed at scale. This perspective reframes the question of 40 not as a rigid evolutionary limit, but as a statistical marker shaped by context. The body was not designed to fail at 40. It was shaped in an environment where reaching that age was uncertain for many. When that uncertainty diminishes, the same biological system demonstrates greater longevity. Yet the trade-offs embedded in its architecture remain visible across extended years. Understanding this continuity between past and present offers insight into the nature of human adaptation. Our species evolved not for a fixed lifespan, but for flexibility within environmental constraints. When constraints change, lifespan patterns change accordingly. The prehistoric rarity of reaching 40 and the modern commonality of extended middle age represent 2 points along the same evolutionary trajectory. The difference lies not in a sudden biological transformation, but in the gradual reshaping of ecological and social conditions. Recognizing this deep continuity invites reflection on how present choices may continue to redefine the boundaries of human life in ways that remain consistent with, yet distinct from, our ancient origins. To understand what the prehistoric pattern of limited longevity means for us today, it is necessary to hold two ideas at once. First, the human body carries deep evolutionary roots shaped in environments where survival beyond 40 was uncertain. Second, the modern world has altered those environments so profoundly that extended lifespan has become common in many regions. The tension between these realities invites careful reflection. When most humans in prehistory never reached 40, it was not because the body possessed a rigid expiration date. It was because cumulative external pressures narrowed the margin for long-term survival. Today, those margins have widened, yet the biological architecture remains largely unchanged. The systems that evolved to manage acute threat now operate in settings where chronic conditions dominate. The stress response that once prepared the body for immediate danger may be activated by social and psychological pressures rather than predators or famine. Metabolic pathways designed to conserve energy during scarcity may function differently in environments of abundance. Immune systems tuned for frequent pathogen exposure may behave unpredictably when infectious burden declines, but inflammatory triggers persist. These dynamics suggest that longevity is not merely a matter of surviving longer, but of navigating a lifespan that extends beyond the ecological assumptions under which our physiology evolved. Modern longevity also changes the meaning of middle age. In prehistoric populations, reaching 40 often signified having endured multiple layers of risk. It marked a threshold crossed by fewer individuals. In contemporary societies, 40 is often considered the midpoint of adult life rather than a rare milestone. This shift influences expectations about career, family, health, and identity. The demographic expansion of middle age creates social structures that support prolonged education, delayed reproduction, and extended economic participation. None of these patterns characterize the majority of human history. They are outcomes of environmental transformation layered upon ancient biology. The extension of lifespan also presents new ethical and practical questions. As populations age, healthcare systems must address chronic diseases that were less prominent when fewer individuals survived into later decades. Social support networks adapt to longer intergenerational overlap. Economic systems adjust to extended working lives and prolonged retirement. These adjustments illustrate that longevity reshapes not only individual experience, but collective organization. The rarity of reaching 40 in prehistory reminds us that extended lifespan is historically contingent rather than biologically guaranteed. It required centuries of innovation in sanitation, nutrition, and medicine. It depends on continued maintenance of those systems. In regions where such infrastructure weakens, mortality patterns can revert toward earlier forms. This fragility underscores the importance of recognizing longevity as an achievement of environmental buffering rather than a permanent biological entitlement. Reflecting on the long arc from Pleistocene landscapes to modern cities clarifies that human lifespan is deeply intertwined with context. Our evolutionary past established the capacity for extended survival, but it did not ensure its widespread realization. The prehistoric demographic profile was shaped by cumulative hazard. The modern profile reflects mitigation of those hazards, yet the same biological trade-offs persist beneath contemporary conditions. Understanding this continuity encourages a measured perspective. Longevity is neither an anomaly nor an inevitability. It is a product of interaction between ancient physiology and changing environment. The story of why most humans in prehistory never reached 40 reveals not a limitation of our species, but the profound influence of ecological constraint. Recognizing that influence invites thoughtful consideration of how present choices will shape the demographic patterns of generations yet to come. If we step back and look across the entire arc of human history, the rarity of reaching 40 in prehistoric populations no longer appears as a mystery. It becomes a reflection of context. For hundreds of thousands of years, human life unfolded within environments defined by ecological instability, high childhood mortality, reproductive risk, injury, infection, conflict, and scarcity. The human body was shaped to endure these pressures long enough to reproduce and sustain small cooperative groups. It was not shaped in a world of reliable sanitation, advanced medicine, and sustained nutritional surplus. When most humans in prehistory did not reach 40, it was because the cumulative weight of those pressures narrowed survival probabilities long before later decades became common experience. The archaeological record, demographic modeling, evolutionary biology, and comparative anthropology all converge on this conclusion. Biological potential for extended life existed. Some individuals clearly survived into their 40s, 50s, and beyond, yet they represented a minority within populations structured by high early mortality and persistent environmental risk. 40 marked not a biological wall, but a statistical threshold fewer people crossed. It was an age earned by navigating layers of vulnerability across childhood, reproductive years, and physically demanding adulthood. The modern world has altered those probabilities dramatically. Through sanitation, vaccination, medical intervention, and improved nutrition, many societies have reduced the hazards that once limited survival. The same biological architecture that struggled under prehistoric constraint now reveals its latent capacity for longer life. Yet this expansion does not erase our evolutionary history. It reminds us that longevity depends not solely on genes, but on the environments we construct and maintain. Extended lifespan is an achievement of collective organization layered upon ancient physiology. Recognizing this continuity carries an educational value. It invites humility about the fragility of longevity. It encourages appreciation for public health systems and social cooperation that sustain modern life expectancy. It also reframes aging not as a defect, but as a stage that few of our ancestors consistently experienced. The presence of extended middle age and old age today is historically unusual, yet biologically possible. The contrast between prehistoric and modern lifespan reveals how deeply human life is shaped by context. Our species evolved to survive uncertainty, to adapt, and to cooperate. When conditions reduce external hazards, survival extends. When hazards accumulate, lifespan contracts. The story of why most humans in prehistory never reached 40 is therefore not a story of biological inadequacy. It is a story of environmental constraint and gradual transformation. It reveals that the boundaries of human life are neither fixed nor entirely self-determined. They emerge from the interaction between ancient bodies and changing worlds. As we continue to reshape our environment through technology and social organization, new questions arise about how long human life may extend and what responsibilities accompany that extension. If longevity has always depended on the balance between biological design and ecological condition, what balance are we now creating for the generations that will follow?